Somewhere in the ancient world there was a final day. The final day a temple was used. The final day a city gate opened. The final day a road carried travellers. For the people living through those moments, the future was unknown. They could not have imagined that centuries later, strangers would stand among the ruins trying to understand what happened. Yet that is exactly what archaeology does. It reconstructs the final traces of worlds that slowly faded from memory. Sometimes the clues are clear, more often they are not. Entire civilizations leave behind monuments but no explanation. Vast construction projects survive while the reasons for building them disappear. And in the silence left behind, the ancient world continues to ask questions that history has not fully answered. Andriake is an ancient harbour on the southwestern coast of present-day Turkey, near the famous city of Myra. At first glance, it appears to be another Roman port scattered with ruins along the Mediterranean. Yet beneath layers of silt and centuries of abandonment lies one of the most intriguing engineering mysteries of the ancient world. Archaeologists have uncovered evidence of a harbour that remained active for more than a millennium. Despite constant sedimentation, earthquakes, changing coastlines, and the logistical challenges of sustaining maritime trade on a massive scale. Even more puzzling, Andriake became a centre of an industry so technologically sophisticated that modern researchers still debate parts of its production process, the manufacture of Tyrian purple dye, one of the most valuable substances of antiquity. The rediscovery of Andriake emerged gradually through archaeological surveys around the ancient harbour basin and extensive excavations conducted during the early 21st century. What researchers expected to find was a typical Roman port serving nearby Myra. What they uncovered instead was an enormous commercial complex containing warehouses, docks, industrial facilities, cisterns, administrative structures, and evidence of specialized manufacturing activities that connected the Eastern Mediterranean to trade networks stretching thousands of kilometers. The first mystery appears before examining a single building. Harbors are fragile systems, rivers deposit sediment, storms reshape coastlines, sea levels fluctuate. Modern ports often require continuous dredging using heavy machinery to remain operational. Yet Andriake functioned for centuries in an environment that should have gradually buried its harbour facilities beneath layers of silt. Geological studies show that sediment accumulation along Mediterranean coastal environments can significantly alter navigable channels over relatively short historical periods. Similar problems affected famous ancient ports such as Ostia near Rome and Ephesus in western Anatolia, both of which eventually lost direct access to the sea because of sedimentation. Andriake somehow maintained its maritime importance long after many comparable ports declined. The harbour basin raises difficult questions about ancient coastal engineering. Archaeologists can identify quays, breakwaters, and harbour installations, but they still struggle to reconstruct the full system that kept maritime traffic functioning. Some researchers suspect that periodic dredging operations occurred. Others suggest that natural currents may have been exploited through carefully selected harbour placement. The challenge is that evidence for such maintenance activities rarely survives. We see the final infrastructure but not the operational knowledge that sustained it. The result is a technological puzzle hidden beneath layers of sediment that accumulated after the harbour's decline. The scale of Andriake's commercial infrastructure deepens the mystery. The most impressive surviving structure is the massive granary built during the reign of Emperor Hadrian. Stretching approximately 64 meters in length and containing multiple storage chambers, the building ranks among the largest Roman granaries preserved anywhere in the Mediterranean. Such facilities were not merely warehouses. They represented critical components of regional food security systems. Grain had to be protected from humidity, pests, fungal contamination, and temperature fluctuations. A single storage failure could threaten thousands of people. Modern engineers studying ancient storage architecture have noted the remarkable effectiveness of passive environmental control systems used by Roman builders. Thick stone walls moderated temperature changes. Ventilation openings encouraged air circulation. Internal layouts reduced moisture accumulation. Yet a significant question remains unresolved. How did ancient builders develop these designs without modern thermodynamics, humidity sensors, or structural modeling software? The granary demonstrates practical knowledge of environmental engineering that appears surprisingly advanced for its era. Similar principles appear in Roman facilities from Egypt to Britain, but Andriake offers one of the clearest surviving examples. Water management presents another engineering puzzle. A major harbour required enormous quantities of fresh water. Sailors arriving after weeks at sea needed supplies. Warehouses required maintenance. Industrial activities consumed significant resources. Yet Andriake occupied a coastal environment where freshwater availability was limited. Archaeologists have identified cisterns, reservoirs, channels, and collection systems designed to capture and store water. The sophistication of these systems suggests long-term planning rather than simple improvisation. Hydraulic engineering has often been called one of Rome's greatest technological achievements. Aqueducts carried water across valleys, pressurized pipelines supplied urban fountains, complex drainage systems protected cities from flooding. Andriake appears to have incorporated elements of this broader hydraulic tradition while adapting to local environmental conditions. However, many components of the original network remain buried or destroyed, leaving researchers with only fragments of the complete system. The visible infrastructure hints at a larger technological landscape that has largely vanished. Yet none of these mysteries rivals the most extraordinary aspect of Andriake, its purple dye industry. Few products in human history have carried the economic and symbolic value of Tyrian purple. Across the Roman Empire, purple garments became symbols of political authority, wealth, and imperial power. Certain shades were so prestigious that their use was restricted by law. Emperors wore purple. Senators displayed purple borders on their garments. The colour became associated with status throughout the Mediterranean world. The source of this extraordinary dye was astonishingly impractical. It came from marine snails, belonging primarily to the Murex family. Archaeological excavations at Andriake have revealed enormous accumulations of crushed shells, providing direct evidence of industrial-scale production. Scientific estimates suggest that producing a single gram of high-quality purple dye could require processing thousands of mollusks. Some historical reconstructions indicate that tens of thousands of shells might be needed to create enough pigment for a single luxury garment. This is where the technological mystery begins. Researchers understand the broad outline of the process. Specialized glands were extracted from the snails. The material underwent controlled decomposition and chemical transformation. Exposure to sunlight triggered additional reactions that altered the pigment's color. Temperature, oxygen levels, processing duration, and environmental conditions all influenced the final result. However, reconstructing the precise ancient technique has proven remarkably difficult. Experimental archaeologists have attempted to recreate Tyrian purple production using surviving historical descriptions. The results are inconsistent. Small variations in processing conditions can produce dramatically different colors, ranging from blue and violet to reddish purple. Modern chemistry explains some of these reactions, yet ancient producers achieved remarkable consistency across centuries of production. This suggests the existence of highly specialized technical knowledge transmitted through generations of craftsmen. The puzzle becomes even more impressive when viewed from an industrial perspective. Imagine coordinating the collection of tens of thousands of marine snails, transporting them to processing facilities, extracting minute quantities of raw material, controlling complex biochemical reactions, and producing a luxury commodity valuable enough to travel across the Mediterranean. This was not a simple craft. It was a sophisticated manufacturing system operating without laboratories, digital instruments, or written industrial manuals. Comparisons with other ancient industries reveal how unusual this achievement was. Roman concrete relied on carefully selected volcanic materials. Egyptian glassmakers controlled temperatures exceeding 1,000 degrees Celsius. Chinese bronze casters mastered complex metallurgical techniques. The purple dye industry of Andriake belongs in the same category of lost technological traditions. The products survive. The exact operational knowledge largely disappeared. Which mystery of Andriake fascinates you the most? Let us know your thoughts in the comments below. Falassarna is a forgotten harbour on the western coast of Crete, Greece. Today its ancient docks lie stranded on dry land, several meters above sea level and hundreds of meters from the shore. That single fact has transformed Falassarna into one of the most remarkable engineering mysteries of the ancient Mediterranean. Unlike famous ports that vanished beneath the sea, Falassarna rose out of it. The site preserves an extraordinary snapshot of ancient harbour technology frozen in time, allowing archaeologists to examine not only how a major Greek port functioned more than 2,000 years ago, but also how its builders solved technical challenges that continue to puzzle researchers. The modern rediscovery of Falassarna began in the 20th century when archaeological surveys revealed unusual stone structures buried beneath farmland west of Crete. Excavations later uncovered harbour basins, fortifications, quays, warehouses, towers, and a narrow entrance channel connecting the harbour to the sea. What initially appeared to be a typical Hellenistic port soon became something far more mysterious. Geological studies demonstrated that the harbour had originally been built at sea level but was suddenly lifted approximately 6 to 9 meters during the catastrophic earthquake of 365 CE, one of the most powerful seismic events known from the Mediterranean world. The uplift preserved the harbour in a condition rarely seen elsewhere. Instead of being submerged and eroded beneath centuries of marine activity, much of its infrastructure remained accessible for direct study. The first mystery concerns the astonishing accuracy of the harbour's original design. Ancient engineers selected a location exposed to some of the most energetic wave conditions in the eastern Mediterranean. Modern coastal engineers understand that building a functional harbour requires balancing dozens of variables simultaneously: wave energy, sediment transport, prevailing winds, storm frequency, water depth, ship draft, coastal currents, and seasonal changes. Today, such calculations are performed using computers, satellite observations, hydrodynamic models, and decades of oceanographic data. Yet, the engineers of Falassarna achieved a remarkably effective harbour design more than 2,000 years ago without any of these technologies. The entrance channel appears carefully positioned to allow access while minimizing direct wave penetration into the basin. The geometry suggests sophisticated empirical knowledge accumulated through generations of observation, but no surviving technical texts explain how such calculations were performed. The greatest engineering mystery of Falassarna, however, may involve a problem that threatens every harbour ever constructed: sedimentation. Harbours naturally attract sediment. Waves transport sand along coastlines. Rivers deposit silt. Storms move enormous volumes of material across shallow seabeds. Over time, these processes gradually fill harbour basins and block navigation channels. Even modern ports spend millions of dollars annually on dredging operations to remain functional. Ancient ports face the same challenge but without powered excavation equipment. Falassarna is particularly puzzling because it operated successfully for centuries in an environment highly vulnerable to sediment accumulation. Geological analyses indicate that the western coast of Crete experiences significant longshore sediment transport. In simple terms, enormous quantities of sand are continuously moved parallel to the shoreline by waves and currents. Under such conditions, harbour entrances can become blocked surprisingly quickly. Some modern marinas require maintenance every year. Yet Falassarna remained an active commercial and military port for generations. Archaeologists continue debating how this was achieved. One possibility involves continuous dredging by human labour. Another proposes that the harbour's geometry was intentionally designed to create self-cleansing water circulation patterns. A third hypothesis suggests the builders exploited local current systems to reduce sediment accumulation naturally. None of these explanations fully account for the available evidence. This unresolved question becomes even more impressive when compared to other ancient maritime centres. The Roman harbour of Portus near Rome required massive engineering interventions and constant maintenance. The harbour complexes of Alexandria struggled with sedimentation throughout antiquity. Many Phoenician and Greek ports gradually became unusable due to silting. Falassarna appears to have resisted these processes far longer than expected. If the harbour incorporated some form of passive sediment management strategy, it would represent a level of coastal engineering sophistication that remains only partially understood. The harbour entrance itself raises additional questions. Excavations revealed evidence of a narrow channel connecting the inner harbour to open water. Measurements suggest that its dimensions were carefully optimised. If the channel was too narrow, navigation would become difficult. If it was too wide, waves could penetrate the harbour and damage vessels. If it was too shallow, larger ships could not enter. If it was too deep, construction costs would increase dramatically. The final design appears to strike a balance between these competing requirements. Such optimization resembles modern engineering processes, yet no one knows exactly how ancient surveyors achieved the necessary precision. Equally mysterious is the apparent understanding of coastal topography demonstrated by the builders. Before constructing a harbour, engineers must possess detailed knowledge of underwater terrain. Modern projects rely on sonar mapping, bathymetric surveys, GPS positioning, and computer-generated models. Ancient engineers had none of these tools. Nevertheless, the placement of Falassarna suggests accurate assessment of seabed conditions, wave exposure, and navigational safety. Researchers still debate what methods Greek engineers used to collect and process such information. Rope sounding techniques certainly existed, but whether these alone could achieve the observed level of planning remains uncertain. The massive stone structures found throughout the harbour complex present another technological puzzle. Large blocks weighing several tons were quarried, transported, positioned, and aligned with impressive accuracy. Some retained stable positions despite centuries of earthquakes, storms, and environmental change. Structural engineers examining ancient Mediterranean harbours often emphasise that durability depends not merely on material strength, but also on load distribution, foundation preparation, and geometric stability. The survival of many Falassarna structures suggests builders possessed practical knowledge of these principles long before the development of formal engineering science. One of the most fascinating aspects of Falassarna is its role as a military harbour. Historical sources indicate that the city became a significant maritime power during the Hellenistic period. Protecting ships required more than walls. Effective naval defense demanded visibility, communication, logistics, and rapid deployment capabilities. The arrangement of towers and defensive structures suggests careful planning. Some researchers have proposed that visual signaling systems linked observation points across the coastline. Such systems existed elsewhere in the ancient world, but the precise configuration at Falassarna remains uncertain. If accurate, they would demonstrate a sophisticated integration of architecture, geography, and military strategy. The earthquake of 365 CE adds another layer to the mystery. Geological evidence suggests that Western Crete experienced one of the largest known tectonic uplifts in the Mediterranean during this event. Estimates indicate vertical displacement of several meters across extensive sections of coastline. The sudden rise effectively stranded the harbour above sea level and ended its maritime function. Yet, paradoxically, this catastrophe preserved evidence that would otherwise have disappeared beneath the sea. Modern archaeologists can walk through portions of the harbour basin, measure structures directly, and analyse engineering features rarely accessible at submerged ports. What do you think? Was Falassarna's long-term success the result of advanced harbour engineering, a lost sediment control technology, or centuries of accumulated maritime knowledge that has disappeared from history? Share your thoughts in the comments below. Dreros is ancient, windswept, and almost forgotten. High in the mountains of eastern Crete, Greece, roughly 600 meters above sea level and overlooking the Gulf of Mirabello, the ruins of Dreros occupy a rugged landscape that seems poorly suited for urban life. Yet, nearly 3,000 years ago, a thriving city emerged here. What survives today appears modest compared to Knossos or Athens, but archaeologists increasingly recognize Dreros as one of the most important laboratories for understanding how advanced technological knowledge survived the collapse of the Bronze Age. The mystery is not simply who lived here. The mystery is how a relatively small community developed engineering, metallurgy, surveying, administration, and architectural techniques, whose sophistication remains only partially understood. The site first attracted scholarly attention in the late 19th century, but major excavations during the early 20th century revealed something extraordinary. Beneath collapsed walls and layers of stone debris emerged evidence of one of the earliest Greek cities of the Iron Age. Archaeologists uncovered temples, civic buildings, inscriptions, retaining walls, reservoirs, and some of the oldest known bronze cult statues ever discovered in Greece. Each discovery answered one question while creating several new ones. The deeper researchers examined Dreros, the more difficult it became to explain how much technical knowledge had survived after the collapse of the Minoan and Mycenaean worlds several centuries earlier. The first puzzle appears before a single building is examined. It is the location itself. Dreros was constructed on steep, uneven mountain terrain. Modern engineers understand the difficulties involved in creating stable urban infrastructure on slopes. Gravity constantly pulls foundations downhill. Seasonal rains accelerate erosion. Earthquakes destabilize retaining walls. Yet the ancient builders transformed this challenging landscape into a functioning city. Large terraces were cut into hillsides, public spaces were leveled, residential districts were organized along controlled elevations. Stone retaining walls distributed enormous loads across unstable terrain. The precision of these modifications raises important questions. Surveying instruments as we know them did not exist. There were no laser levels, satellite positioning systems, or modern measuring equipment. Yet many of the city's structures exhibit alignments that suggest systematic planning rather than gradual, uncoordinated growth. Researchers estimate that some retaining systems moved thousands of tons of stone and soil. Even more remarkable, Portions of these systems survived nearly 3 millennia in one of the most seismically active regions of the Mediterranean. Crete sits near the boundary between the African and Eurasian tectonic plates. Throughout history, powerful earthquakes have repeatedly struck the island. Ancient cities were damaged, rebuilt, and sometimes abandoned entirely. Yet many walls at Dreros demonstrate surprising resilience. Their construction techniques reveal a sophisticated understanding of structural behavior. Instead of relying solely on rigid masonry, builders often employed layered stone arrangements that distributed stress through multiple points of contact. Small stones filled gaps between larger blocks, creating flexibility within apparent rigidity. This principle resembles earthquake-resistant techniques later observed in Inca architecture at Machu Picchu and Sacsayhuaman. The civilizations were separated by oceans and more than 2,000 years of history, yet both appear to have discovered similar engineering solutions. Whether the builders of Dreros consciously designed for seismic resistance remains debated, but the evidence suggests practical knowledge gained through generations of observation and adaptation. Nothing at Dreros, however, has generated more fascination than the Temple of Apollo and the remarkable bronze statues discovered within it. The temple itself appears relatively modest in scale, but its contents transformed scholarly understanding of early Greek metallurgy. Excavations revealed 3 hammered bronze figures representing Apollo, Artemis, and Lato. These statues date to approximately the late 8th century BCE and rank among the oldest large-scale bronze cult images ever found in Greece. At first glance, they seem simple compared with the masterpieces of classical Greece produced centuries later. Closer examination tells a different story. Metallurgical analysis reveals controlled manufacturing processes requiring significant technical expertise. The bronze sheets were carefully shaped, joined, reinforced, and assembled into coherent anthropomorphic forms. Achieving this required precise control of temperature, alloy composition, hammering techniques, and structural support systems. The challenge becomes apparent when compared with modern metalworking principles. Bronze typically melts between approximately 950 and 1050 degrees Celsius, depending on composition. Maintaining consistent temperatures without modern furnaces, thermometers, or controlled fuel systems demands extensive practical knowledge. Too little heat and the metal cannot be shaped effectively. Too much heat risks structural damage and oxidation. The craftsmen responsible for the Dreros statues operated within narrow tolerances despite lacking scientific instruments. Even more intriguing is the historical timing. These statues appear during a period traditionally associated with recovery from the Greek Dark Age. Conventional narratives often describe this era as a technological decline following the collapse of Bronze Age palace civilizations around 1200 BCE. Yet the Temple of Apollo suggests that significant metallurgical expertise survived. The question is how? Did technical knowledge pass continuously through local workshops? Were there forgotten networks of craftsmen preserving specialized skills? Or does the traditional model of cultural decline underestimate the complexity of post-Bronze Age societies? The mystery deepens when considering the broader economic system required to support such production. Bronze requires copper and tin, metals rarely found together. Tin sources in particular were often located hundreds or even thousands of kilometers from manufacturing centers. The existence of these statues implies participation in long-distance exchange networks extending across the Mediterranean. Somehow, a mountain city on Crete remained connected to technological and commercial systems far larger than itself. The famous legal inscription of Dreros introduces another dimension of complexity. Carved into stone during the 7th century BCE, it is often regarded as one of the earlier surviving constitutional laws in the Greek world. The inscription limits how frequently an individual could hold the office of kosmos, a senior civic position. While historians focus on its political significance, the technological implications are equally remarkable. Written law requires infrastructure. Someone must create standardized writing systems. Someone must preserve records. Someone must enforce regulations across generations. Such systems depend on literacy, administration, and institutional continuity. The inscription suggests that Dreros possessed organizational capabilities far beyond what many would expect from a relatively small Iron Age community. It represents not merely a legal document, but evidence of information technology in its ancient form. Urban planning offers further clues. Unlike settlements that evolved organically over centuries, Dreros displays signs of deliberate spatial organization. Civic spaces, religious structures, residential districts, and circulation routes appear integrated into a coherent design. This level of planning implies surveying techniques capable of measuring distances, establishing orientations, and controlling construction across large areas. Ancient surveyors likely relied on ropes, sightlines, plumb bobs, and geometric principles, yet many details remain uncertain. Archaeologists can identify the final results, but rarely the procedures used to achieve them. This pattern appears repeatedly throughout ancient engineering. The structures survive, the manuals do not. Water management remains one of Dreros' mysteries. Despite its high mountain location and seasonal rainfall, the city survived for centuries, suggesting effective systems for collecting, storing, and distributing water. Archaeological remains indicate the use of reservoirs, cisterns, channels, and gravity-fed networks. However, much of this infrastructure has vanished, leaving only limited evidence of how the system fully operated. Perched on a prominent hill overlooking central Scotland near Bathgate, Cairnpapple Hill appears at first to be little more than a grassy mound surrounded by earthworks. Yet beneath the surface lies evidence of nearly 4,000 years of continuous ceremonial activity. Long before Stonehenge reached its final form, generations of people returned to this hilltop, reshaping it again and again. Archaeologists can identify the monuments they built, the graves they dug, and the structures they left behind. What remains difficult to explain is how prehistoric communities repeatedly demonstrated levels of planning, surveying, astronomical observation, and long-term knowledge preservation that seem remarkably sophisticated for societies without writing, metal instruments, or formal mathematics. The modern story of Cairnpapple began in the 1940s when large-scale excavations led by archaeologist Stuart Piggott revealed a sequence of monuments hidden beneath the hill. What appeared to be a single burial mound turned out to contain layers of construction representing multiple eras of prehistory. Excavations uncovered ceremonial circles, post holes, burials, stone settings, and later Bronze Age tombs. Each generation had modified the landscape while preserving the site's importance. Instead of a single monument, Cairnpapple emerged as a record of thousands of years of engineering decisions. One of the greatest mysteries concerns the selection of the hill itself. Cairnpapple rises approximately 312 metres above sea level and commands panoramic views across much of central Scotland. Modern digital terrain analysis shows that the location offers exceptional visibility over surrounding landscapes. Today, such position could be identified through satellite imagery, GIS software, and topographic surveys. 5,000 years ago, none of those technologies existed. Yet prehistoric builders somehow selected one of the most strategically prominent locations in the region. Researchers continue to debate whether this choice was purely symbolic or based on practical surveying knowledge. Similar questions arise at other major prehistoric centres such as Stonehenge in England and Newgrange in Ireland. In all three cases, builders appear to have selected locations possessing unusual visibility, horizon characteristics, or astronomical potential. Some archaeologists suggest that prehistoric surveyors may have developed sophisticated landscape assessment techniques that are poorly understood today. The challenge is that such knowledge would leave almost no direct archaeological evidence. The earliest phases of Cairnpapple included large circular arrangements marked by timber posts. Today, the wood has vanished completely, leaving only stains and post holes in the soil. Reconstructing these circles reveals a surprising degree of geometric regularity. The spacing between posts appears deliberate rather than random. Creating such layouts on uneven terrain without modern measuring tools would have required practical geometry. Experimental archaeologists have demonstrated that circles can be created using ropes and central reference points. However, this explanation raises additional questions. Rope-based geometry still requires standardized measurements, planning, and coordination. Someone had to establish consistent lengths and maintain accuracy across the entire construction process. Similar mysteries surround prehistoric circles across Britain, where builders repeatedly achieved impressive geometric precision centuries before formal mathematical texts existed in Europe. The construction of ritual pits at Cairnpapple presents another engineering puzzle. Excavations revealed deep features cut into the underlying geology. Digging such structures using stone, antler, and bone tools would have demanded enormous labour. Modern calculations suggest that even relatively small ceremonial excavations could require hundreds of work hours. Yet the pits were often placed with remarkable consistency relative to other features within the monument. This implies a level of planning extending beyond simple excavation. Builders appear to have understood how to organize labor, establish reference points, and maintain spatial relationships over time. Such capabilities resemble basic surveying practices found in much later civilizations. The tools were simpler, but the underlying principles may have been surprisingly advanced. Perhaps the most astonishing aspect of Cairnpapple is the continuity of construction across millennia. Archaeological evidence indicates that successive generations repeatedly built over earlier monuments. Timber circles gave way to stone settings. Ceremonial enclosures evolved into burial monuments. Bronze Age tombs appeared within areas already considered sacred for centuries. The time separating these phases was often hundreds of years. In some cases, entire cultural traditions had changed. Yet builders consistently retained awareness of important locations within the site. The central zones remained significant despite the passage of many generations. This creates one of the most difficult questions in prehistoric archaeology. How was knowledge transmitted across centuries without written records? Modern societies preserve technical information through documents, maps, and archives. Neolithic communities relied entirely on oral traditions. Somehow, information regarding sacred locations, construction layouts, and ceremonial practices survived for periods longer than the entire history, separating the Norman conquest from the present day. The geometric organization of Cairnpapple provides additional evidence of technical sophistication. Surveys indicate that many features conform to circular or near-circular arrangements. While modern observers often underestimate the difficulty of constructing accurate circles, engineers recognize that even simple geometry requires reliable reference systems. Comparisons with Stonehenge are revealing. Studies of Stonehenge suggest builders maintained alignment errors measured in only a few degrees despite transporting stones weighing up to 25 tons. Cairnpapple's structures were smaller, yet they display similar concerns with spatial order and symmetry. The recurring appearance of geometric planning across multiple prehistoric sites suggests that practical surveying traditions may have been widespread throughout Neolithic Britain. The most intriguing mystery, however, involves astronomy. Many researchers have investigated whether Cairnpapple's layout incorporates celestial alignments. Although consensus remains elusive, several features appear oriented towards significant points on the horizon. Certain alignments may correspond to sunrise or sunset positions during particular times of the year. Others potentially relate to major lunar standstills, rare astronomical events occurring approximately every 18.6 years due to the Moon's orbital cycle. If these alignments were intentional, the implications are extraordinary. Tracking lunar standstills requires observations spanning nearly 2 decades. No individual observation session could reveal the pattern. Instead, generations would need to record and remember horizon positions over long periods. This level of astronomical monitoring rivals achievements documented at sites such as Stonehenge, the Callanish Stones and Newgrange. Modern astronomical software allows researchers to reconstruct ancient skies. Some simulations suggest that horizon markers visible from Cairnpapple may have served as observational reference points. Yet proving intentionality remains challenging. Were these alignments deliberate engineering decisions or coincidental outcomes of construction? Archaeologists continue debating the evidence. Nevertheless, the possibility raises profound questions about prehistoric knowledge systems. Astronomy was not merely about observing the sky, it required measurement, memory, prediction, and communication. A community capable of tracking celestial cycles over decades possessed a form of scientific knowledge, even if it was never written down. The burials at Cairnpapple add another layer of complexity. During the Bronze Age, important graves were placed within the existing ceremonial landscape, often in central or symbolic locations. This suggests later communities still understood the site's earlier layout. Whether through surviving markers or cultural memory, such continuity points to effective ways of preserving knowledge across generations. Banasa is a forgotten Roman city on the banks of the Cebu River in northern Morocco. At first glance, it appears to be little more than a collection of ruined walls scattered across a fertile plain. Yet beneath these stones lies one of the least discussed engineering mysteries of the Roman world. Archaeologists have spent more than a century excavating its streets, public buildings, workshops, and hydraulic systems, but many of the technologies that allowed Banasa to flourish remain only partially understood. Unlike famous Roman centres such as Pompeii or Leptis Magna, Banasa rarely appears in popular documentaries. However, its location presents a challenge that may be even more intriguing. The city was built on an active floodplain beside one of Morocco's largest rivers, a landscape where seasonal flooding, unstable soils, and constant sediment deposition should have made long-term urban construction extremely difficult. Yet Banasa survived for centuries, maintaining roads, drainage systems, monumental architecture, and public infrastructure in an environment that constantly threatened to destroy them. The ruins first attracted serious archaeological attention during the French Protectorate period in the early 20th century. Systematic excavations revealed a surprisingly organized Roman colony, covering roughly 10 hectares, with evidence of occupation stretching from the Mauritanian kingdom into the Roman imperial era. Beneath layers of accumulated sediment, archaeologists uncovered paved streets, administrative buildings, baths, temples, houses, workshops, and an extensive water management network. The discoveries immediately raised questions. How had Roman engineers transformed such a challenging landscape into a functioning city? More importantly, how much of the technical knowledge behind that achievement has disappeared? One of the first mysteries concerns surveying technology. Banasa was planned according to the Roman grid system, with major streets intersecting at carefully controlled angles. Creating such geometric precision sounds straightforward today, but Roman surveyors lacked modern instruments. No laser levels, electronic distance meters, satellite positioning systems, or digital mapping tools existed. Yet the city's alignment remained remarkably consistent across hundreds of meters. Similar precision has been documented at Roman colonies throughout the Mediterranean, but Banasa presents a special challenge because of its terrain. Floodplain landscapes shift over time. Sediment accumulates unevenly. Ground levels change after major floods. Maintaining geometric accuracy under such conditions required a level of surveying expertise that historians still struggle to reconstruct completely. The challenge becomes even greater when considering drainage. Banasa stood beside the Cebu River, whose basin covers approximately 40,000 square kilometers. Seasonal fluctuations could dramatically alter local water levels. A city built too low would flood. A city built too high would struggle to access water resources efficiently. Excavations have revealed underground drains, channels, and carefully graded streets, designed to direct runoff away from residential districts. The gradients appear subtle yet effective. Modern civil engineers calculate such slopes using mathematical models and hydrological simulations. Roman engineers relied entirely on observation, experience, and practical measurement. The fact that their system functioned for generations suggests a sophisticated understanding of hydraulic behavior that remains only partially documented in surviving Roman texts. The floodplain itself introduces another engineering puzzle. Much of the ground surrounding Banasa consists of alluvial deposits created by centuries of river activity. Such soils are often prone to settlement and instability. Modern construction on similar terrain frequently requires deep foundations, soil reinforcement, or extensive geotechnical analysis. Yet many structures at Banasa maintain their integrity for centuries. Archaeological evidence suggests that builders deliberately prepared foundation layers, using combinations of compacted materials designed to distribute loads more effectively. Whether these techniques resulted from formal engineering principles or centuries of accumulated practical knowledge remains uncertain. What is clear is that Roman builders repeatedly succeeded in environments where modern engineers would proceed with caution. The movement of construction materials represents another unresolved question. Banasa was not located directly beside major stone quarries. Large public buildings required enormous quantities of masonry, bricks, lime, timber, and roofing materials. Even a medium-sized Roman bath complex could consume thousands of tons of construction resources. Transporting such quantities across ancient landscapes demanded sophisticated logistics. Historians can identify probable supply routes and estimate labor requirements, but the exact organizational mechanisms remain largely invisible. The ruins preserve the finished structures. The transportation systems, management practices, and workforce coordination that made those structures possible have mostly vanished. Among all the mysteries surrounding Banasa, perhaps none is more fascinating than the technology hidden within its mortar and concrete. For decades, scientists have studied Roman construction materials throughout the Mediterranean and repeatedly encountered an uncomfortable fact. Many ancient mortars continue to survive after nearly 2,000 years, while numerous modern concretes begin deteriorating after only a few decades. Banasa provides another example of this puzzle. Analysis of Roman mortars from various sites has revealed complex mixtures containing lime, volcanic materials, crushed ceramics, sand, and other aggregates. Chemical reactions within these materials sometimes continued long after construction was completed. In certain cases, microscopic mineral crystals formed over time, strengthening the structure instead of weakening it. Modern researchers studying Roman concrete from harbours in Italy have identified self-healing properties capable of sealing small cracks through ongoing mineral growth. Banasa does not possess the famous marine concrete of Roman ports such as Caesarea Maritima or Cosa, yet its surviving masonry demonstrates remarkable durability despite centuries of weathering, seasonal moisture, temperature fluctuations, and biological activity. What makes the mystery even deeper is that the exact recipes varied from region to region. Roman builders often adapted materials to local resources. This means Banasa likely employed construction formulas specifically tailored to northern Morocco. Archaeologists can identify components through laboratory analysis, but reconstructing the precise manufacturing process remains difficult. Questions persist regarding firing temperatures, mixing ratios, curing techniques, water content, and quality control procedures. How are these recipes transmitted? Were they written down, taught through apprenticeships, or guarded as trade secrets? The historical record provides only fragments of the answer. Comparisons with modern concrete reveal why the issue remains important. Ordinary Portland cement, the foundation of most contemporary construction, typically generates micro cracks over time due to thermal stress, chemical reactions, and environmental exposure. Engineers designed structures expecting gradual deterioration and maintenance. Yet some Roman mortars appear to gain resilience as they age. Studies of ancient materials have identified mineral formations such as calcium, aluminum, silicate hydrates, and recrystallized lime inclusions that may contribute to long-term durability. These discoveries have inspired modern materials scientists to investigate whether aspects of Roman technology could improve sustainable construction today. In this sense, Banasa is not merely an archaeological site. It is a laboratory preserving clues to engineering solutions that modern society may still be trying to rediscover. The city's water infrastructure introduces another layer of complexity. Access to water was essential not only for drinking but also for bathing, industry, agriculture, and sanitation. Excavations suggest an integrated system combining drainage, storage, and distribution. Yet significant portions remain buried or poorly preserved. Researchers can map fragments of the network, but often struggle to reconstruct its complete operation. This uncertainty resembles challenges encountered at Roman cities elsewhere, including Volubilis and Timgad. We can observe the surviving channels. We cannot always see the operational logic that connected them into a functioning urban system. Itanos is a forgotten city on the far eastern coast of Crete, Greece, where the land meets the Aegean Sea in a landscape of rock, wind, and salt. Today only scattered ruins remain, but beneath the shoreline lies one of the most intriguing engineering mysteries of the ancient Mediterranean. Archaeologists discovered that much of the ancient harbour system appears to have vanished. Portions of the city now lie underwater, and the infrastructure that once connected Itanos to international trade networks stretching from Egypt to the Levant has largely disappeared. Yet historical evidence suggests that for centuries Itanos was a prosperous maritime centre. The mystery is not why the city declined. The mystery is how a coastal settlement built in one of the most geologically unstable regions of the Mediterranean managed to operate a sophisticated harbour, maintain water supplies, survive earthquakes, and sustain long-distance commerce without any of the technologies modern engineers consider essential. The ruins of Itanos attracted scholarly attention during the 19th century, but systematic archaeological investigations expanded significantly during the 20th century. Excavations revealed Hellenistic, Roman, and Byzantine occupation layers, imported ceramics from distant regions, monumental architecture, and evidence of extensive maritime activity. What researchers expected to find was a typical ancient port city. What they found instead was a puzzle. The economic evidence suggested a harbour of major regional importance. Yet, the physical remains of that harbour seem surprisingly limited. The discrepancy between what the city achieved and what survives today has become one of the site's most fascinating mysteries. The greatest enigma surrounding Itanos is the harbour itself. Ancient trade was impossible without maritime infrastructure. Merchant vessels crossing the eastern Mediterranean required safe anchorage, loading facilities, storage areas, repair capabilities, and protection from storms. Historical records and archaeological finds indicate that Itanos participated in commercial networks spanning hundreds and sometimes thousands of kilometers. Imported goods arrived from Egypt, Cyprus, and the Levant. Such activity implies a harbour capable of handling substantial maritime traffic. Yet much of that infrastructure has either vanished beneath the sea or remains unidentified. This creates an engineering paradox. Economic evidence indicates the existence of a highly functional port system, while archaeological evidence preserves only fragments of its physical structure. Modern researchers attempting to reconstruct the harbour face numerous unanswered questions. Where were the main breakwaters? How were docking facilities organised? What methods were used to protect ships from seasonal storms? Why do the surviving remains appear insufficient for the scale of commerce suggested by the archaeological record? The mystery deepens when underwater investigations are considered. Divers and marine archaeologists have identified submerged walls, structures, and architectural fragments offshore. Some features now lie below sea level despite having originally been constructed on dry land. Their existence suggests that significant geological changes occurred after construction. The challenge is determining precisely what happened. Did tectonic activity gradually lower portions of the coastline? Did earthquakes cause sudden subsidence events? Did long-term sea level changes slowly consume sections of the harbour? Or did multiple processes operate simultaneously over centuries? Crete sits near the boundary between the African and Eurasian tectonic plates, one of the most seismically active zones in Europe. Major earthquakes have repeatedly reshaped coastlines throughout the eastern Mediterranean. The famous earthquake of 365 CE generated a tsunami that affected regions across the Mediterranean basin. Geological studies indicate that portions of Crete experienced dramatic vertical land movements during antiquity. Some coastal areas were uplifted several meters while others subsided. Itanos may preserve evidence of similar processes, but reconstructing the exact sequence remains extraordinarily difficult. What makes this particularly fascinating is that ancient engineers somehow built a functioning maritime city within this unstable environment. Modern coastal engineers rely on satellite mapping, computer simulations, bathymetric surveys, and geological modelling to evaluate shoreline risks. Ancient builders possessed none of these tools. Nevertheless, Itanos operated successfully for centuries. The question is not merely how they constructed harbour facilities, it is how they identified suitable locations in the first place. The city's urban layout raises equally intriguing questions. Itanos occupies a narrow coastal zone constrained by hills and the sea. Designing a settlement under such conditions requires careful consideration of drainage, transportation routes, water access, and building stability. Even small surveying errors could create major problems. Yet archaeological evidence suggests a relatively organised urban landscape rather than chaotic development. This implies the existence of surveying knowledge far more sophisticated than often assumed. Comparison with other Mediterranean ports highlights the challenge. At sites such as Alexandria, Caesarea, Maritima, and Piraeus, substantial harbour remains help researchers reconstruct ancient engineering practices. In Itanos, however, much of the critical infrastructure appears either destroyed, buried, submerged, or hidden beneath later deposits. The result is similar to attempting to understand a modern airport after the runways have disappeared while the passenger records remain intact. Water management presents another major puzzle. Eastern Crete experiences long dry periods and receives significantly less rainfall than many other regions of Greece. Sustaining a population of several thousand people would have required reliable access to fresh water. The challenge becomes even greater when one considers visiting merchants, sailors, livestock, workshops, and agricultural activity. Archaeological evidence points to cisterns, reservoirs, and water control systems, but the full network remains unclear. The mathematics of water supply reveal the scale of the problem. A population of only 3,000 residents consuming a modest 20 litres of water per day would require approximately 60,000 litres daily. Over a year, that equals nearly 22 million litres. Actual requirements were likely much higher when commercial activities are included. Such figures suggest an infrastructure system capable of capturing, storing, and distributing enormous quantities of water, yet only fragments of that system survive. Some researchers suspect that the inhabitants exploited local groundwater resources and seasonal runoff with remarkable efficiency. Others propose that now vanished channels and collection systems once extended beyond the visible ruins. Whatever the answer, the surviving archaeological remains probably represent only a fraction of the original hydraulic network. Construction technology introduces another layer of mystery. Many walls at Itanos survived centuries of earthquakes, storms, erosion, and human activity. Crete experiences frequent seismic events, making structural resilience essential. Ancient builders lacked reinforced concrete, steel frames, and modern engineering calculations. Yet numerous structures endured long enough to leave recognizable remains after more than 2,000 years. This durability recalls engineering puzzles seen elsewhere in the ancient world. The polygonal masonry of the Andes, the earthquake-resistant foundations of certain Japanese castles, and the flexible stone construction found in parts of the Greek world all demonstrate that ancient builders often develop solutions through empirical knowledge, rather than theoretical science. Itanos may represent another example of such practical engineering wisdom. The problem is that the knowledge itself has vanished, leaving only the results behind. Modern ports depend on software, communication systems, logistics networks, and specialized infrastructure. Ancient ports depended on human knowledge performing similar functions. Every imported amphora, every foreign ceramic vessel, and every traded commodity discovered at Itanos serves as evidence of an invisible administrative system that archaeology can only partially reconstruct. Karphi is perched high in the Dictys Mountains of eastern Crete, Greece, more than 1,100 meters above sea level. The site was first identified by British archaeologists in the early 20th century, and systematic excavations led by J.D.S. Pendlebury during the 1930s revealed something unexpected. Scattered across a rugged mountain ridge were the remains of one of the largest refuge settlements of the late Minoan world. At first glance, Karphi appears to be merely another abandoned hilltop village. Yet the deeper archaeologists investigated, the more puzzling it became. The settlement emerged during one of the most turbulent periods in Mediterranean history, shortly after the collapse of the Bronze Age civilizations around 1200 BCE. Palaces fell, trade networks disintegrated, and major centres across the eastern Mediterranean were abandoned. Somehow, while much of the known world was descending into instability, a substantial community established itself on an isolated mountain peak and survived for generations. The mystery is not simply why Karphi existed. The mystery is how its inhabitants managed to construct, organise, and sustain such a complex settlement in an environment that seems fundamentally hostile to urban life. Karphi occupies a naturally defensible position overlooking the Lassithi Plateau and large portions of eastern Crete. Modern visitors reaching the site quickly understand the challenge faced by its ancient inhabitants. The terrain is steep, rocky and difficult even with modern hiking equipment. Every building stone, every storage vessel, every tool and every daily necessity had to be transported uphill. Archaeologists estimate that hundreds of structures once occupied the settlement. Houses, shrines, storage areas, workshops, pathways, terraces, and communal spaces covered the mountain slopes. The logistical effort required to establish such a community raises questions that remain unanswered. Comparable refuge settlements appeared elsewhere in Crete during the same period, including Kavousi Castro, but Karphi was considerably larger and more densely occupied. It resembles less a temporary sanctuary and more a functioning mountain city. One of the greatest engineering mysteries concerns the settlement's planning. Karphi was not built randomly. Excavations revealed neighbourhoods arranged along natural contours, interconnected pathways, and carefully positioned structures adapted to difficult terrain. Modern engineers facing a similar landscape would conduct geological surveys, slope analyses, and structural calculations before construction. The builders of Karphi possessed none of these technologies, yet many of their buildings remained stable for more than 3,000 years. Large retaining walls supported terraces carved into the mountainside. These terraces created usable construction platforms where none naturally existed. The precision with which these foundations were integrated into the landscape suggests a sophisticated understanding of slope stability gained through experience rather than formal mathematics. Archaeologists can identify the results, but the practical techniques used to select locations, calculate loads, and prevent collapse remain largely unknown. Water presents an even greater puzzle. Every permanent settlement depends on reliable access to water, yet Karphi sits far from major rivers and lakes. Modern hydrological studies suggest that a community of several hundred to perhaps more than 1,000 people would have required substantial water resources throughout the year. Seasonal rainfall alone appears insufficient to explain long-term occupation. Researchers have proposed that the inhabitants collected rainwater using extensive storage systems, but relatively few large reservoirs have been identified. Another possibility involves springs that may have flowed more strongly during the Late Bronze Age than they do today. Climate conditions in Crete have changed significantly over the past 3 millennia, complicating attempts to reconstruct ancient water availability. Similar questions arise at mountain settlements such as Machu Picchu in Peru, where sophisticated water management systems sustained large populations in difficult terrain. Unlike Machu Picchu, however, Karphi has yielded little direct evidence explaining how water distribution functioned. The infrastructure that made survival possible remains largely invisible. Food production creates another unresolved problem. Mountain environments generally limit agricultural potential, yet Karphi persisted for multiple generations. The settlement's population required grain, livestock, olive products, and other resources in quantities large enough to sustain daily life. Archaeological evidence suggests connections with lower elevations, indicating that food likely arrived through organized supply systems. However, transporting agricultural products uphill on a regular basis would have demanded significant labor and coordination. Comparisons with other refuge communities across the Mediterranean show that many remained relatively small due to logistical constraints. Karphi exceeded these expectations. Some scholars argue that the settlement maintained strong economic links with communities occupying more fertile regions. If true, this implies a level of political organization and regional cooperation often underestimated for the so-called Greek Dark Age. The survival of Minoan cultural traditions at Karphi presents another mystery. The settlement dates to a period after the collapse of the famous Minoan palatial system, associated with sites such as Knossos, Vaistos, and Malea. Normally, when complex societies collapse, technical knowledge begins to disappear. Architectural standards decline, artistic quality deteriorates, and specialized crafts become increasingly rare. Yet Karphi provides evidence that important aspects of Minoan culture continue to survive. Excavations uncovered religious figurines, ceremonial objects, and architectural forms strongly connected to earlier Minoan traditions. Among the most famous discoveries are clay figurines depicting female deities with raised arms, an iconic feature of Minoan religious practice. Their presence indicates cultural continuity, extending generations beyond the destruction of the palaces. This continuity raises difficult questions about knowledge transmission. How did specialized skills survive in an age of political fragmentation? Craft production requires trained artisans. Construction techniques require experienced builders. Religious traditions require teachers and communities capable of preserving complex rituals. Written records from Karphi are virtually non-existent, meaning knowledge must have been transmitted directly from person to person. Similar processes occurred following the collapse of the Western Roman Empire, when many engineering techniques survived through apprenticeship rather than written manuals. Karphi may represent an earlier example of the same phenomenon. The challenge is that archaeology rarely preserves the knowledge itself. It preserves only the products created by that knowledge. The location of Karphi also suggests the possibility of advanced communication networks. The settlement commands extensive views across eastern Crete. Modern visibility analyses demonstrate that multiple mountain peaks and valleys can be observed from the site. Some researchers have suggested that visual signaling systems using smoke, fire, or reflective surfaces may have linked communities across large distances. Comparable systems existed elsewhere in the ancient world. Classical Greek city-states employed beacon chains for military communication. The Byzantine Empire later developed signaling networks stretching hundreds of kilometers. If Karphi participated in a similar system centuries earlier, it would indicate a surprisingly sophisticated approach to regional security and information exchange. Unfortunately, direct evidence remains elusive. Perhaps the most intriguing mystery involves why Karphi existed at all. Traditional explanations describe it as a refuge settlement established by people fleeing instability after the Bronze Age collapse. While partially convincing, this theory leaves important questions unanswered. Refugee camps are usually temporary. Karphi was not. Its architecture, planning, and long-term occupation indicate that its inhabitants expected to remain for generations. They invested enormous labor into construction projects that would have made little sense for a short-term sanctuary. This suggests that Karphi represented more than a place of refuge. It may have functioned as a deliberate strategy for preserving communities, traditions, and knowledge during an era of uncertainty. Scientific dating places Karphi between the 12th and 10th centuries BCE, a poorly understood period in Greek history. While much of the eastern Mediterranean experienced population decline, reduced trade, and political collapse, Karphi adapted and endured. The settlement shows that even during societal collapse, knowledge, skills, and communities can survive. though the reasons often remain unclear in the archaeological record. On the summit of Dunadd, an ancient hill fort in Argyll, western Scotland, once stood the royal centre of the Gaelic kingdom of Dalriata between the 6th and 8th centuries CE. Archaeologists investigating this rocky fortress uncovered an extraordinary feature carved directly into the bedrock. A human footprint roughly 27 centimetres long, accompanied by a rock-cut basin, carved symbols, and traces of ceremonial activity. At first glance, the footprint appears simple, yet this small carving has become one of the most intriguing technological and ceremonial mysteries of early medieval Europe. Unlike castles, churches, or monuments, its purpose seems to have been symbolic rather than practical. Evidence suggests it played a role in royal inauguration ceremonies, but the engineering knowledge, surveying methods, landscape planning, and political symbolism behind its creation remain only partially understood. More than 1,000 years later, researchers can measure the stone, map the site, and analyze its surroundings, yet many questions remain unanswered. The first mystery concerns the footprint itself. Carving a recognizable human foot into hard bedrock is more difficult than it appears. Experimental archaeology demonstrates that shaping stone with early medieval iron tools requires significant labor and precision. The Dunadd footprint is not merely a shallow depression created by erosion. It possesses a deliberate shape, including a heel, arch, and toes. The proportions are remarkably realistic. Researchers estimate that the carving was intended for an adult male standing upright during a ritual. The question is how craftsmen achieved such accuracy without modern measuring instruments. Comparable footprints associated with inauguration rituals have been identified in Ireland, particularly at sites linked to early Gaelic kingship. However, each example differs slightly, suggesting that no universal template existed. If craftsmen worked freehand, the accuracy is impressive. If they used measuring systems or wooden guides, those tools have completely disappeared. The footprint becomes even more intriguing when viewed within its wider landscape. Dunadd rises from a marshy plain and dominates surrounding routes through western Scotland. From the summit, visibility extends across large sections of Kilmartin Glen and nearby waterways. Modern topographic analysis shows that the site occupies an exceptionally strategic position. The placement of the footprint appears intentional rather than random. During inauguration ceremonies, a ruler standing within the carved foot would have faced the surrounding territory. Medieval Irish texts describe kings symbolically placing a foot upon sacred stones to demonstrate union with the land. The Dunadd footprint may represent a physical manifestation of that tradition. Yet, archaeologists still debate whether its exact orientation was chosen for political symbolism, astronomical considerations, or visual control of the landscape. The mystery deepens because the footprint does not exist alone. Nearby archaeologists identified a carved basin known as a rock-cut cistern, along with inscriptions and symbols incised into the bedrock. Some researchers believe the basin held water used during inauguration rituals. Others suggest it served practical functions unrelated to kingship. Chemical analysis has failed to identify residues capable of proving either theory conclusively. Similar ritual basins appear at early medieval sites across Ireland and Scotland, but their exact functions remain controversial. The association between the basin and footprint suggests a coordinated ceremonial complex rather than isolated carvings. If so, Dunadd preserves evidence of a sophisticated ritual landscape whose full meaning has been lost. One of the greatest technological puzzles involves how the inhabitants modified the summit itself. Dunadd occupies a steep volcanic outcrop rising approximately 30 meters above the surrounding terrain. Archaeological excavations reveal multiple defensive walls, terraces, gateways, and occupation areas constructed across difficult slopes. Building such a fortress required extensive knowledge of terrain engineering. Modern surveys indicate that walls were carefully positioned to exploit natural defensive advantages while minimizing construction effort. This level of planning resembles optimization strategies used in later medieval castles. Yet Dunadd predates many of those fortifications by centuries. Researchers can identify the final results, but still struggle to reconstruct the planning methods used by the builders. Excavations have also uncovered evidence of advanced metalworking. Archaeologists discovered molds, crucibles, metalworking debris, and fragments of high-status objects. Scientific analysis identified production involving bronze, silver, and gold. Some decorative items demonstrate levels of craftsmanship comparable to prestigious artifacts from Ireland and Anglo-Saxon England. The presence of such industries raises difficult logistical questions. Raw materials had to be transported to a relatively isolated hilltop. Skilled artisans required training, tools, and access to trade networks. Chemical studies of metal compositions indicate connections extending far beyond Western Scotland. Dunadd appears to have functioned not merely as a fortress, but as a centre of technological production. Yet the organisational systems that supported these activities remain largely invisible. The footprint also raises questions about measurement and standardisation. Modern researchers often assume that symbolic carvings are artistically informal. However, detailed scans of the Dunadd footprint reveal proportions consistent with a realistic human foot rather than an abstract symbol. This suggests intentional design choices. Ancient builders across Europe frequently employed practical measurement systems based on body parts such as feet, cubits, or handspans. The Roman foot measured approximately 29.6 centimeters. The Dunadd footprint falls surprisingly close to dimensions used in several historical measurement traditions. Whether this similarity is coincidental or deliberate remains unknown. If deliberate, the carving may have embodied a standard unit of authority as well as a symbol of kingship. Another mystery concerns knowledge transmission. The inauguration traditions associated with Dunadd appear linked to broader Gaelic cultural practices. Similar royal footprints have been documented at ancient inauguration sites in Ireland. The existence of related ceremonies across the Irish Sea implies the movement of specialised knowledge between regions. Such knowledge may have included ritual procedures, stone carving techniques, surveying methods, and political symbolism. Maintaining these traditions across generations required reliable systems of education, despite the absence of widespread written records. Modern historians can trace similarities between sites, but cannot fully explain how this knowledge was preserved with such consistency. Recent digital mapping has revealed additional complexity. High-resolution terrain models suggest that Dunadd's builders carefully integrated natural rock formations into defensive and ceremonial structures. Certain pathways channel movement towards significant locations, including the summit area containing the footprint. This resembles architectural strategies found at much larger ceremonial centres. Comparisons have been drawn with sites such as the Hill of Tara in Ireland, where ritual movement through the landscape played an important symbolic role. While Dunadd is considerably smaller, the underlying principles may have been similar. The challenge is that archaeology preserves stones and pathways, but rarely preserves the ideas that govern their arrangement. The footprint may have served as a form of political technology. While modern societies use constitutions and institutions to legitimize power, early medieval rulers often relied on symbolic rituals. By placing his foot in the carved footprint, a king turned authority into a public visible act. The stone helped create legitimacy, while the rituals and meanings surrounding it have largely been lost. In eastern Crete, Greece, near the modern village of Kritsa, about 10 kilometers from the Gulf of Mirabello, the ancient city of Lato emerged through systematic excavations that began in the late 19th century. At first glance, the ruins appear less impressive than Knossos, Phaistos, or the great cities of classical Greece. Yet archaeologists increasingly view Lato as one of the most intriguing engineering puzzles of the ancient Mediterranean. Built between two steep rocky hills, roughly 300 meters above sea level, the city flourished from the 7th century BCE until the Roman period. More than 2,500 years later, researchers can map its streets, measure its walls, and analyze its reservoirs. But many of the technological systems that allowed thousands of people to survive and prosper in such a difficult environment remain only partially understood. The first mystery begins with the location itself. Ancient cities usually emerged beside rivers, fertile plains, or natural harbours. Athens had access to Praisos. Corinth controlled strategic trade routes. Alexandria stood beside one of the world's most productive river systems. Lato had none of these advantages. Instead, its inhabitants selected a rugged mountain ridge with steep slopes and limited water resources. From a modern engineering perspective, it appears to be one of the least practical locations imaginable for a major settlement. Yet archaeological evidence shows that the city grew into one of the most important Doric centres of eastern Crete. Standing among the ruins today, visitors encounter an urban plan that appears remarkably organised despite the terrain. Streets, stairways, public buildings, defensive structures, and residential districts were integrated into the landscape with surprising efficiency. This raises an important question. How did ancient surveyors achieve such precision without modern instruments? Even small measurement errors would have multiplied across the steep hillsides, creating major structural problems. Instead, many terraces remain aligned after more than 2 millennia. Similar challenges can be seen at Machu Picchu in Peru or Monte Alban in Mexico, where builders transformed mountainous terrain into functioning cities. Lato demonstrates that Greek engineers possessed comparable abilities to reshape difficult landscapes through careful planning and surveying. Water presents an even greater mystery. Crete experiences long dry seasons, and Lato lacked direct access to a major river or permanent freshwater lake. Modern estimates suggest that a population of several thousand people would have required hundreds of thousands of litres of water each month for drinking, cooking, sanitation, and craft production. Archaeologists have identified large cisterns, drainage systems, channels, and collection basins throughout the city. These structures demonstrate sophisticated rainwater harvesting techniques. Yet the complete hydraulic system remains uncertain. Some researchers believe undiscovered reservoirs may still exist beneath collapsed structures. Others suggest that groundwater sources were exploited using techniques that left little archaeological evidence. Whatever the answer, the city sustained itself for centuries in an environment where water should have been a constant limitation. The engineering of the reservoirs themselves creates another puzzle. Water storage sounds simple until one considers the technical requirements involved. Reservoir walls had to resist hydrostatic pressure, prevent leakage, and survive seasonal temperature changes. Even minor failures could contaminate supplies or destroy infrastructure. Laboratory analysis of surviving construction materials indicates careful stone selection and sophisticated mortar use. Similar hydraulic challenges were solved in other ancient societies, including Nabatea and Petra and Roman North Africa. Yet Lato achieved its solutions centuries before Roman hydraulic engineering reached its peak. the exact methods used by local builders remain incompletely understood. Stoneworking provides another remarkable mystery. Throughout the city, enormous blocks were quarried, transported, shaped, and assembled with impressive accuracy. Some retaining walls consist of stones weighing several tons. The challenge is not simply cutting the stone. The greater question is how those blocks were moved across steep mountainous terrain. Experimental archaeology demonstrates that moving multi-ton blocks even short distances requires substantial labour and coordination. Ancient Egyptian pyramid builders relied on sledges, prepared surfaces, and massive workforces. At Lato, the terrain was far less forgiving. No definitive evidence survives showing precisely how construction crews transported heavy materials from quarry sites to elevated building locations. The city's defensive architecture reveals additional technical sophistication. Lato occupied a naturally defensible position, yet its builders enhanced those advantages through careful design. Gates, walls, and elevated observation points created overlapping defensive zones. Modern military analyses suggest that attackers would have been forced into narrow approaches where defenders enjoyed clear tactical superiority. Similar principles appear in later fortifications such as Mycenae and even medieval castles. The mystery lies in the level of geometric planning required. Builders appear to have understood visibility, movement corridors, and defensive depth with remarkable effectiveness, despite lacking formal military engineering manuals. Earthquake resistance may be one of the most overlooked mysteries at Lato. Crete lies near the boundary between the African and Eurasian tectonic plates and has experienced destructive earthquakes throughout recorded history. Many ancient settlements across the eastern Mediterranean suffered repeated seismic damage, yet significant portions of Lato survived. Engineers studying ancient structures have noted the strategic use of bedrock foundations, thick retaining walls, and flexible construction layouts adapted to local geology. Similar empirical earthquake-resistant techniques have been identified in Inca architecture, Japanese castle foundations, and certain Roman structures. Whether Lato's builders intentionally incorporated seismic knowledge or arrived at these solutions through generations of observation remains unknown. The city's public architecture presents another unanswered question. The agora, administrative structures, and temples required levels of organization extending beyond simple construction skills. Building projects of this scale demand planning, logistics, resource allocation, workforce management, and long-term maintenance. Historians often focus on surviving monuments, but the true technological achievement may have been administrative rather than architectural. Every stone placed in the correct location implies systems of measurement, communication, supervision, and quality control. These invisible systems rarely survive in the archaeological record. Archaeologists have also been puzzled by evidence of economic activity that appears larger than expected for a mountain city. Pottery finds, imported goods, and trade connections indicate participation in wider Mediterranean networks. Goods arrived from regions hundreds of kilometers away. Maintaining such connections required transportation systems, storage facilities, accounting practices, and commercial coordination. Although no written records survive explaining these processes, the material evidence demonstrates that Lato functioned as part of a complex economic landscape rather than an isolated hilltop settlement. Scientific studies continue to reveal clues. Digital terrain modeling has helped researchers reconstruct ancient movement routes. Geological analysis identifies probable quarry sources. Hydrological simulations estimate water collection capacities. Architectural surveys generate highly accurate three-dimensional models of surviving structures. Yet despite these modern tools, many essential questions remain unresolved. researchers can measure outcomes with extraordinary precision, but the practical knowledge behind those achievements has largely disappeared. Along the southwestern coast of modern Turkey, near the Mediterranean shoreline of ancient Lycia, lie the remarkable ruins of Patara, once one of the most sophisticated cities of the ancient world. Beneath sand dunes and marshland, archaeologists uncovered a massive harbour, a parliament building, aqueducts, warehouses, monumental gates, and the remains of what is believed to be the world's oldest known Roman lighthouse. Yet the greatest mystery of Patara is not what survived. It is the technological knowledge that disappeared. The city flourished for more than 1,000 years, serving as the principal port of Lycia and later one of the most important maritime centres of the Roman Empire. Today, researchers can map its streets and analyse its stones with lasers and satellite imagery. But many of the engineering systems that allowed Patara to function remain only partially understood. Patara's greatest puzzle begins with its harbour. Ancient writers described it as one of the busiest ports in the eastern Mediterranean. The city occupied a strategic position connecting maritime trade routes between Egypt, Greece, the Levant, and Anatolia. Yet modern visitors find no active harbour. Instead, the ancient waterfront lies several kilometres inland. Geological studies show that sediment carried by the Xanthos River gradually filled the harbour basin over centuries. This process is understandable. What remains difficult to explain is how Patara maintained a functioning port for so long despite this constant threat. Harbour silting destroys maritime infrastructure worldwide. Even modern ports require expensive dredging operations using industrial machinery. Ancient Patara appears to have remained operational for centuries. Researchers suspect large-scale dredging, channel management, or hydraulic interventions may have been employed, but direct evidence remains limited. If such systems existed, they would represent a level of environmental engineering comparable in complexity to the harbour maintenance programs later seen at Roman Portus near Rome. The harbour raises another logistical mystery. During its peak under Roman rule, Patara likely handled thousands of tons of cargo annually. Grain, olive oil, wine, marble, timber, metals, and luxury goods moved through its docks. Every ship required loading facilities, storage systems, administrative oversight, labour coordination, and navigation infrastructure. Modern ports rely on computers, communications networks, and sophisticated logistics software. Patara relied entirely on human expertise. Archaeologists have recovered warehouses and commercial buildings, but the invisible administrative system that coordinated maritime trade has vanished. The city functioned as an enormous economic machine, yet most of the knowledge that powered that machine disappeared without leaving written technical manuals. One of the most remarkable discoveries at Patara emerged in 2020 when archaeologists reconstructed the monumental Roman lighthouse, originally built during the reign of Emperor Nero, around AD 64. Standing approximately 26 meters tall, the structure is among the earliest known Roman lighthouses whose architectural details can be reconstructed with confidence. Thousands of fallen stone blocks were recovered and digitally analysed. The reconstruction revealed extraordinary precision. Individual blocks were cut and positioned with engineering accuracy that rivals some later medieval masonry. The mystery is not that Roman engineers could build such a lighthouse. Numerous ancient examples existed, including the famous Lighthouse of Alexandria. The puzzle is how they achieved such durability in a seismically active region. Southwestern Anatolia sits near multiple tectonic fault systems. Earthquakes repeatedly struck the region throughout antiquity. Yet the lighthouse survived for many centuries before eventually collapsing. structural analysis suggests sophisticated load distribution through interlocking stone courses. Some engineers compare these techniques to earthquake-resistant features observed in certain Inca structures at Machu Picchu, where precisely fitted stone blocks dissipate seismic energy more effectively than rigid masonry. The city's water management system presents another technological enigma. Patara occupied a region characterized by hot Mediterranean summers and seasonal rainfall variability. Sustaining an urban population potentially exceeding 15,000 inhabitants required a dependable water supply. Archaeologists have documented aqueducts, reservoirs, cisterns, pipelines, and distribution networks extending throughout the city. Hydraulic calculations indicate that maintaining sufficient water pressure across varying elevations would have required precise gradients. Modern engineers know that even small errors in slope can dramatically reduce efficiency in gravity-fed systems. Roman surveyors possessed instruments such as the chorobates and groma, but the accuracy achieved in many ancient water systems continues to impress modern researchers. Similar questions surround Roman aqueducts at Segovia in Spain and Pont du Gard in France. Patara joins this list of sites demonstrating hydraulic expertise that often appears surprisingly advanced for a pre-industrial society. The Parliament building of the Lycian League introduces a different kind of mystery. The structure is one of the most important surviving assembly halls from the ancient world and has attracted attention from historians because the Lycian League influenced later political thinkers, including some involved in drafting the United States Constitution. Yet engineers are equally fascinated by the building's acoustic performance. Modern studies of ancient theatres frequently reveal remarkable sound transmission characteristics. In Patara's assembly hall, speakers could address large audiences without amplification. Architectural geometry appears to have enhanced vocal clarity while reducing echoes. Whether ancient architects understood acoustic principles theoretically or developed them through generations of experimentation remains uncertain. Similar questions arise at Greek theatres such as Epidaurus, where whispers can reportedly be heard dozens of meters away under favourable conditions. Another unresolved question involves construction logistics. Patara contains thousands of tons of stone architecture. Monumental gates, temples, public baths, warehouses, administrative buildings, and defensive structures required vast quantities of material. Quarrying, transporting, shaping, and assembling these stones demanded enormous labour resources. Experimental archaeology demonstrates that moving multi-ton stone blocks without modern machinery is possible. The challenge lies in efficiency. Patara's construction program extended over centuries and involved repeated urban expansion. Researchers estimate that some public buildings required the placement of hundreds or even thousands of precisely cut blocks. Comparable challenges were faced at Baalbek in Lebanon, where some stones exceeded 800 tons, and at the Roman harbour of Caesarea Maritima, where massive construction transformed an exposed coastline into an artificial port. Patara may not match those projects in scale, but its cumulative engineering achievements suggest highly organised construction systems whose operational details remain poorly understood. The city's relationship with sand creates yet another mystery. Large portions of Patara gradually disappeared beneath shifting dunes. Ironically, the same natural processes that buried the city also help preserve it. Archaeologists continue uncovering structures concealed for centuries beneath layers of windblown sediment. Geological evidence indicates significant environmental changes occurred throughout antiquity. Coastlines migrated, wetlands expanded and contracted, navigation channels altered course. Yet the inhabitants repeatedly adapted. Understanding exactly how they monitored and responded to these environmental transformations remains difficult because most of the practical knowledge involved would have been transmitted orally. Similar challenges confronted ancient settlements near Ephesus, where harbour silting ultimately contributed to urban decline. Patara appears to have resisted these forces longer than many comparable ports. Scientific investigations have provided important clues. Ground-penetrating radar, satellite mapping, sediment core analysis, digital reconstruction, and geoarchaeological surveys reveal increasing detail about the city's development. Researchers can model harbour evolution, reconstruct trade routes, estimate cargo capacity, and analyse building stability. Yet technology has also highlighted how much remains unknown. The more accurately Patara's systems are reconstructed, the more impressive they appear. The city integrated maritime infrastructure, water management, political architecture, transportation networks, environmental adaptation, and long-distance commerce into a single urban system that functioned successfully for centuries. Nuku Hiva stone sites are scattered across the remote island of Nuku Hiva in the Marquesas archipelago of French Polynesia, more than 1,400 kilometers northeast of Tahiti in the Central Pacific. Their existence was known to local communities for centuries, but systematic archaeological investigation only accelerated during the 20th century as researchers began documenting the island's monumental stone platforms, ceremonial complexes known as meiai, massive retaining walls, terraces, and enigmatic tiki statues carved from volcanic rock. What archaeologists discovered was unexpected. On an isolated island with no metal tools, no wheeled transport, no draft animals, and limited natural resources, ancient builders created some of the most sophisticated stone constructions in Polynesia. The mystery is not whether these structures exist. They stand today across valleys and mountainsides. The mystery is how a relatively small island population developed engineering solutions capable of transforming one of the most rugged volcanic landscapes in the Pacific into a network of monumental architectural complexes whose construction methods remain only partially understood. The first challenge begins with geography itself. Nuku Hiva covers approximately 340 square kilometers and consists largely of steep volcanic terrain cut by deep valleys and dramatic cliffs. Modern visitors often struggle to reach many archaeological sites, even with contemporary roads and vehicles. Yet ancient builders somehow transported enormous quantities of stone across this difficult landscape. Excavations reveal ceremonial platforms extending dozens of meters in length and constructed from carefully selected basalt blocks, weighing hundreds of kilograms and, in some cases, multiple tons. Unlike the civilizations of Egypt, Mesopotamia, China, or Rome, the inhabitants of Nuku Hiva possessed neither iron tools nor complex machinery. They operated within what archaeologists classify as a non-metallic technological system. Nevertheless, they reshaped entire hillsides. The scale of landscape modification remains one of the greatest puzzles. Many meiai were not simply placed on naturally flat ground. Builders first transformed steep slopes into engineered terraces. This required excavation, levelling, drainage management, and the construction of retaining walls capable of resisting soil pressure and tropical erosion. Modern geotechnical engineers recognize that slope stabilization is among the most difficult forms of construction, because mistakes often result in landslides or structural collapse. Yet many of Nuku Hiva's ancient terraces have survived for centuries despite intense rainfall, tropical vegetation growth, earthquakes, and erosion. The achievement invites comparison with the agricultural terraces of the Inca in Peru or the mountain engineering of the Ifugao rice terraces in the Philippines. However, unlike those societies, the Marquesan builders left no written records explaining their methods. The retaining walls themselves present another technical mystery. Numerous structures employ dry stone construction, meaning no mortar binds the stones together. Instead, stability depends entirely on the selection, shaping, and placement of individual blocks. Archaeologists studying these walls have noted remarkably effective load distribution. Larger stones often form the foundation, while carefully fitted intermediate layers reduce stress concentrations. In some locations, the walls remain stable after hundreds of years of exposure to environmental forces. This durability is particularly surprising because volcanic islands experience repeated cycles of moisture expansion, root intrusion, and ground movement. Similar dry stone techniques appear in places such as Machu Picchu and certain Mediterranean fortifications, yet direct cultural connections are impossible. The resemblance suggests that different societies independently discovered advanced structural principles through observation and experimentation. Perhaps nowhere is ancient craftsmanship more visible than in the island's stone sculptures. Nuku Hiva contains numerous tiki statues carved from basalt, one of the hardest volcanic rocks commonly available to ancient peoples. Some statues exceed 2 meters in height and display symmetrical facial features, detailed anatomical forms, and stylistic consistency that implies highly skilled specialists. Experimental archaeology has attempted to replicate such work using stone tools comparable to those available to ancient Polynesians. Results indicate that carving even a single large basalt figure would require enormous labor investment and exceptional technical expertise. Yet multiple sites contain concentrations of statues that suggest production occurred on a scale larger than previously assumed. Researchers continue debating how artisans achieved such precision, how long individual sculptures required to complete, and how finished monuments were transported across difficult terrain. The transportation problem becomes even more intriguing when population estimates are considered. Before European contact, estimates for the population of the Marquesas vary widely, ranging from tens of thousands to perhaps over 80,000 inhabitants across the archipelago. Even under higher estimates, the labor required to quarry, transport, and assemble thousands of tons of stone represents a substantial organizational challenge. Modern construction projects rely on cranes, steel cables, vehicles, and surveying instruments. Ancient Marquesans relied on human coordination. This implies sophisticated social systems capable of mobilizing large workforces, allocating resources, and transmitting technical knowledge across generations. The architecture therefore serves not only as evidence of engineering, but also as evidence of complex administration. The mystery deepens when researchers examine the spatial distribution of archaeological sites. Rather than concentrating exclusively around a single political centre, monumental structures appear across numerous valleys throughout the island. Surveys have documented extensive networks of ceremonial platforms, residential terraces, agricultural modifications, and stone monuments. This distribution suggests that engineering knowledge was not confined to a single elite workshop. Instead, expertise may have been widely shared among multiple communities. Such decentralization raises questions about how technical information circulated. Without writing systems, knowledge transfer depended entirely upon oral traditions, apprenticeship, and practical experience. Yet the consistency observed in construction techniques indicates surprisingly reliable transmission over long periods. Another unresolved question concerns surveying methods. Modern engineers use levels, measuring instruments, and mathematical calculations to establish horizontal surfaces and structural alignments. The builders of Nuku Hiva possessed none of these technologies in a modern sense. Nevertheless, many ceremonial platforms exhibit impressive geometric regularity. Walls remained straight over considerable distances. Terraces maintained stable elevations. Structural components align in ways that appear intentional rather than accidental. Archaeologists suspect the use of highly refined observational methods involving chords, sight lines, wooden markers, and accumulated practical experience. However, direct evidence for these techniques remains scarce because organic surveying tools rarely survive in tropical environments. Some researchers have also investigated possible astronomical dimensions of site planning. Polynesian navigators were among the greatest seafarers in human history, crossing thousands of kilometers of open ocean using observations of stars, ocean swells, winds, and bird behavior. The settlement of the Marquesas itself represents a remarkable technological accomplishment. Certain ceremonial complexes appear oriented towards significant solar positions or landscape features that may have held cosmological importance. While evidence remains debated, the possibility raises fascinating questions. If the same observational knowledge used for long-distance navigation influenced architectural planning, then Nuku Hiva's monuments may preserve traces of an integrated scientific tradition linking astronomy, ritual, and engineering. The maritime context may ultimately represent the greatest technological mystery of all. Before any stone platform could be built, people first had to reach one of the most isolated island groups on Earth. Genetic, linguistic, and archaeological evidence indicates that Polynesian voyagers traversed vast ocean distances long before European navigators entered the Pacific. Reaching the Marquesas required voyages of thousands of kilometers across waters lacking visible landmarks. Experimental voyages using reconstructed traditional canoes have demonstrated that such journeys are possible, but they also highlight the extraordinary navigational expertise required. In many ways, the stone monuments of Nuku Hiva may be secondary achievements compared to the maritime knowledge that brought their builders there. The ancient ruins of Guarda stand on the Atlantic coast of northwestern Spain near the modern town of Guarda in Galicia. The site, known today as Santa Trega, was first brought to serious archaeological attention in 1913, when systematic excavations began, revealing hundreds of stone structures buried beneath vegetation on the slopes of Monte Santa Trega. Rising approximately 341 meters above sea level and overlooking the mouth of the Minho River where Spain meets Portugal, the settlement immediately challenged existing assumptions about Iron Age Europe. Archaeologists expected to find a modest hill fort. Instead, they uncovered evidence of one of the largest and most sophisticated Castro settlements ever discovered in the Iberian Peninsula. More than a century later, researchers can map its streets, measure its walls, analyze its artifacts, and estimate its population. Yet some of the engineering knowledge that allowed this mountaintop city to flourish remains surprisingly difficult to explain. The first mystery begins with scale. Excavations have identified hundreds of circular and rectangular stone buildings spread across a vast area. Estimates suggest that at its peak between the 1st century BCE and the 1st century CE, Santa Trega may have housed several thousand inhabitants. This places it among the largest known settlements of the Castro culture. The challenge is understanding how such a large population functioned on a steep mountainside. Modern urban planners rely on surveying instruments, topographic maps, and engineering calculations to design settlements on difficult terrain. The builders of Santa Trega possessed none of these technologies, yet the settlement displays evidence of organized planning, carefully arranged residential sectors, circulation routes, and defensive zones integrated into the natural landscape. One of the most intriguing technological puzzles involves terrain modification. Monte Santa Trega is not a naturally flat plateau. Much of the settlement occupies sloping ground. Before houses could be constructed, large sections of the mountain had to be stabilized and reshaped. Archaeologists have identified artificial terraces and retaining structures that allowed entire neighborhoods to exist, where natural conditions would have made construction difficult. Even today, engineers working on steep slopes must account for erosion, soil movement, water infiltration, and long-term structural stability. Santa Trega experiences heavy Atlantic rainfall, often exceeding 1,500 millimeters annually in parts of Galicia. Over 2,000 years, such conditions should have destroyed poorly designed foundations, yet many of the terraces remain recognizable. Researchers understand the physical structures, but the methods used to evaluate slope stability and drainage remain largely invisible. Water management presents another mystery. Every permanent settlement depends on reliable control of water. Too little water threatens survival. Too much water destroys infrastructure. The Atlantic climate of northwestern Iberia creates precisely this challenge. During periods of intense rain, uncontrolled runoff can trigger erosion and destabilize foundations. Archaeologists have found evidence suggesting that builders carefully considered drainage when positioning structures. However, most water control systems were likely constructed from perishable materials or have been destroyed by centuries of weathering. As a result, researchers can observe the successful outcome but not necessarily the techniques that produced it. Similar problems appear at Iron Age hillforts in Britain and Oppidas across continental Europe. Yet Santa Trega's position on a steep maritime mountain makes its long-term stability particularly remarkable. The famous circular houses of Santa Trega introduce another engineering question. Circular architecture appears repeatedly throughout Atlantic Europe, from Scottish broch settlements to ancient communities in Ireland. Traditional explanations often focus on culture or aesthetics. Engineers, however, recognize practical advantages. Circular structures distribute stress more evenly than rectangular buildings. They eliminate weak corner points and improve resistance to strong winds. On an exposed mountain overlooking the Atlantic Ocean, such advantages could have been significant. Wind tunnel studies conducted on circular structures in modern architecture demonstrate measurable reductions in pressure concentration compared with comparable square designs. Whether the inhabitants understood these principles theoretically is unlikely, yet generations of empirical observation may have produced architectural solutions that effectively exploited aerodynamic advantages without formal scientific knowledge. Construction logistics raise equally difficult questions. The settlement required enormous quantities of stone. Even conservative estimates suggest that thousands of tons of material were extracted, transported, shaped, and assembled. Modern calculations of labor investment at comparable Iron Age sites indicate that constructing a medium-sized stone dwelling could require hundreds of person-days of work. Multiplied across hundreds of buildings, the total labor requirement becomes immense. There is no evidence of cranes, metal lifting machinery, or advanced transport systems. Every stone had to be moved using human and animal power. This implies an organizational capacity far greater than the stereotype often applied to prehistoric societies. Researchers continue to debate whether construction occurred gradually over generations, or whether centralized leadership coordinated major building phases. The defensive system presents another puzzle. Santa Trega occupies a naturally strong position overlooking critical maritime and riverine routes. archaeological evidence indicates the presence of walls and controlled access points. The mountain commands extraordinary visibility across the surrounding region. On clear days, observers can monitor coastal approaches, river traffic, and movement across the landscape. Some researchers have proposed that settlements throughout the region may have formed interconnected observation networks capable of transmitting information through smoke signals, fires, or reflected light. Similar signaling systems are historically documented in many parts of the world, including Roman frontier defences and medieval beacon chains. Yet proving such a network archaeologically remains extremely difficult. The geography strongly suggests the possibility, but direct evidence remains elusive. Trade introduces another layer of complexity. Excavations have recovered imported Roman materials, indicating that Santa Trega participated in wider economic networks extending far beyond Galicia. The settlement occupied a strategic location near the Minho estuary, one of the most important natural corridors in northwestern Iberia. Goods moving between inland communities and Atlantic maritime routes could pass through this region. Successful participation in such networks required more than roads and boats. It required systems of storage, accounting, exchange, scheduling, and security. Modern logistics depends on software and communications technology. Ancient societies relied entirely on human knowledge. The physical evidence of trade survives. The administrative systems that made trade possible have largely disappeared. Perhaps the most surprising mystery concerns standardization. Archaeologists have noted recurring construction patterns throughout the settlement. Building techniques, wall styles, and spatial organization often display remarkable consistency. Such consistency suggests the existence of shared construction knowledge transmitted across generations. Yet Iron Age Galicia left no written engineering manuals. No architectural plans survive. No technical instructions have been discovered. Everything had to be learned through observation, apprenticeship, and experience. This raises an important question. How was technical knowledge preserved with sufficient accuracy to maintain construction standards over centuries? Similar problems appear throughout the ancient world, from the polygonal masonry of the Andes to the earthquake-resistant timber traditions of Japan. The structures survive. The knowledge systems that created them often do not. Nestled in the mountains of eastern Crete, Greece, a few kilometers inland from the modern town of Sitia, Praisos stands as one of the island's most intriguing archaeological sites. It was identified during 19th century explorations and later excavated by British archaeologists who uncovered fortifications, temples, houses, inscriptions, and evidence of a civilization that seemed strangely different from the rest of the Greek world. Praisos is widely regarded as the last major centre of the Eteocretans, a people whom ancient Greek writers themselves described as the original inhabitants of Crete. More than a century of archaeological research has revealed the city's walls, streets, and artifacts. Yet behind every stone lies a technological mystery. Researchers can map the ruins, measure the architecture, and analyze the materials. But many of the engineering systems that allowed Praisos to survive for centuries remain only partially understood. The first mystery begins with geography itself. Praisos was not built on a fertile plain, a major harbour, or a river valley. Instead, the city occupied a series of steep hills rising above rugged terrain. The settlement spread across multiple ridges separated by natural depressions, creating a defensive position that offered extensive visibility across eastern Crete. Such locations were militarily advantageous, but extremely difficult for urban development. Modern topographic surveys show that builders had to adapt construction to irregular slopes while maintaining structural stability. Similar challenges appear at sites such as Machu Picchu in Peru or Monte Alban in Mexico, where engineers transformed mountainous landscapes into functional urban centres. At Praisos, however, the methods used to achieve this transformation remain uncertain. Archaeologists can identify terraces and retaining walls, but the surveying techniques that allowed builders to align structures across uneven terrain have disappeared. The city's fortifications present another puzzle. Massive defensive walls once surrounded parts of the settlement, protecting inhabitants from both local rivals and external invasions. Some surviving sections consist of enormous stone blocks fitted together with remarkable precision. Unlike modern construction, no steel reinforcement existed, and mortar use appears limited in several sections. Yet portions of these defences endured earthquakes, erosion and warfare for more than 2,000 years. Crete sits near the boundary between the African and Eurasian tectonic plates, one of the most seismically active regions in Europe. Earthquakes exceeding magnitude 7 have repeatedly struck the island throughout recorded history. Despite these conditions, many ancient structures survived far longer than engineers might expect. This raises an important question. Did the builders possess practical knowledge of earthquake-resistant construction acquired through centuries of observation? Similar debates surround the polygonal masonry of the Andes and the flexible stonework found in parts of the ancient Mediterranean. Praisos may represent another example of empirical engineering knowledge that was never written down. Water management creates an even greater mystery. Eastern Crete experiences long, dry summers and highly variable rainfall. Any substantial population required reliable water supplies throughout the year. Archaeologists have identified cisterns and storage facilities, but the full hydraulic system remains elusive. Ancient urban centres often depended on sophisticated water technologies. The city of Knossos utilized drainage channels more than 3,000 years ago. Roman cities later constructed aqueducts capable of transporting millions of litres daily. Praisos appears to have functioned successfully without comparable monumental infrastructure. This suggests the existence of local solutions specifically adapted to the environment. Some researchers suspect extensive rainwater harvesting systems once operated across rooftops and terraces. Others propose underground reservoirs that have not yet been identified. Whatever the answer, the surviving evidence indicates a level of hydraulic planning greater than the visible remains alone would suggest. The agricultural economy supporting Praisos remains equally enigmatic. Estimates based on settlement size suggest that thousands of inhabitants occupied the region during its peak periods. Feeding such a population required efficient food production and storage systems. Yet the surrounding landscape offers limited agricultural potential compared with many Mediterranean plains. Ancient farmers somehow transformed challenging terrain into productive land capable of supporting urban life. Terrace agriculture likely played an important role. Similar systems elsewhere in the Mediterranean dramatically increased arable area while reducing soil erosion. However, many ancient terraces around Praisos have vanished through centuries of abandonment and natural degradation. Archaeologists therefore observe the results of a successful agricultural system without fully understanding the techniques that sustained it. Trade introduces another layer of complexity. Although Praisos was inland, it participated in regional exchange networks connecting eastern Crete to the wider Mediterranean. Imported pottery, metals, and luxury goods reveal contact with distant communities. Maintaining such connections required roads, transport systems, storage facilities, and administrative coordination. Ancient logistics often remain invisible because organic materials rarely survive. Yet every imported object discovered at Praisos implies a chain of activities involving merchants, pack animals, warehouses, and record keeping. Modern supply networks depend on software and communication systems. Ancient networks depended on human knowledge performing similar organizational functions. The physical artifacts survive, the operational knowledge does not. Among the most fascinating discoveries are the inscriptions written in the Eteocretan language. Several texts recovered from Praisos preserve one of the last surviving traces of a language that remains largely undeciphered. Linguists can read the Greek alphabet used to write many of these inscriptions, but understanding the language itself is far more difficult. Unlike Egyptian hieroglyphs or Linear B, Eteocretan lacks sufficient bilingual texts to allow complete interpretation. This creates a profound technological mystery. Written language represents information technology. It stores knowledge beyond human memory and allows administrative systems to function across generations. If Eteocretan literacy survived for centuries, schools, scribes, and methods of knowledge transmission must also have existed. Yet the institutional framework supporting this literacy remains almost entirely invisible archaeologically. Religious architecture at Praisos provides additional evidence of sophisticated planning. Temples and ceremonial areas occupied prominent positions within the settlement. Their placement appears deliberate, often taking advantage of visibility, orientation, and landscape features. Similar patterns occur at Greek sanctuaries throughout the Aegean. However, researchers continue debating how ancient builders established alignments and measurements without modern instruments. Even simple orientation requires consistent surveying methods. Reproducing such accuracy across generations implies technical traditions that extended far beyond individual craftsmen. The metallurgy practiced by the inhabitants also raises unanswered questions. Bronze and iron artifacts recovered from the site demonstrate access to specialized manufacturing knowledge. Producing quality metal tools requires precise control of temperature, fuel, or preparation and cooling processes. Ancient metallurgists achieved these results without thermometers, chemical analysis, or modern furnaces. Experimental archaeology repeatedly demonstrates how difficult such production can be. The existence of reliable metal tools at Praisos therefore reflects accumulated expertise developed through centuries of experimentation. Unfortunately, the workshops reveal only fragments of that process. Widan el-Faras, isolated in the desert north of Egypt's Fayum Depression, looks like little more than a bare basalt outcrop. Yet hidden among its black volcanic stone lies evidence of one of the most astonishing industrial operations of the ancient world. More than 4,500 years ago, during the age when the pyramids were rising along the Nile, Egyptian engineers developed a quarrying and transportation system capable of extracting thousands of tons of hard basalt from a remote desert and delivering it to royal construction projects hundreds of kilometers away. The mystery is not that the quarry existed. The mystery is how such a sophisticated logistical network functioned with a level of planning, surveying, and engineering that remains only partially understood today. The modern rediscovery of Widan el-Faras transformed understanding of ancient Egyptian industry. Archaeological surveys conducted in the 20th century revealed extensive quarry remains scattered across the basalt plateau. More surprising was the discovery of an ancient paved transport road extending approximately 11 to 12 kilometers across the desert. Researchers eventually recognized that this was not an ordinary road. It may represent one of the oldest engineered freight roads ever discovered anywhere on Earth. Suddenly, Widan el-Faras was no longer simply a quarry. It became evidence of a large-scale industrial landscape operating during the Old Kingdom, the same era responsible for monuments such as the Great Pyramid. The first puzzle begins with the basalt itself. Ancient Egypt possessed abundant limestone deposits close to the Nile Valley. Limestone was easier to quarry, easier to transport, and available in enormous quantities. Yet royal builders repeatedly chose to obtain basalt from one of the harshest and most inaccessible regions of northern Egypt. The decision suggests that ancient engineers possessed a sophisticated understanding of material properties. Basalt is significantly harder than limestone. On the Mohs hardness scale, limestone typically ranges between 3 and 4, while basalt commonly reaches values around 6. Its density often approaches 2.8 to 3.0 metric tons per cubic meter. The stone resists wear, survives heavy traffic, and maintains polished surfaces far longer than softer alternatives. Such characteristics made basalt ideal for temple pavements, ceremonial floors, and architectural elements subjected to constant use. The question is how ancient planners evaluated these advantages thousands of years before the emergence of modern geology or materials science. The quarrying process itself presents another unresolved mystery. Basalt is notoriously difficult to work. Modern quarries frequently rely on steel tools, explosives, hydraulic equipment, and diamond cutting systems. Ancient Egyptian quarry workers possessed none of these technologies. During much of the Old Kingdom, copper remained the primary metal available for tools. Copper is substantially softer than basalt. Archaeologists generally believe workers used dolerite hammerstones to fracture the rock and employed quartz-rich sand as an abrasive during cutting and shaping operations. Experimental archaeology demonstrates that such methods can work, yet scale remains the challenge. Widan el-Faras was not producing a few ceremonial objects. Evidence suggests sustained extraction on an industrial level. Thousands of tons of basalt appear to have left the quarry over centuries. The mystery is not whether ancient workers could cut basalt. The mystery is whether the known techniques can fully explain the speed, efficiency, and production volume implied by the archaeological record. Equally remarkable is the logistical system hidden behind the quarry. Widan el-Faras lies in an environment that receives little rainfall and offers few natural resources for large groups of workers. Every quarry operation required food, water, tools, replacement equipment, shelter, and transportation. Maintaining such an operation would have demanded careful planning and administrative coordination. Comparisons can be made with Roman imperial quarries, such as Mons Claudianus in Egypt's eastern desert. However, many of those Roman operations were established nearly 2,000 years later and benefited from administrative systems that are much better documented. At Widan el-Faras, the organizational mechanisms remain largely invisible. The workers are gone, the records are scarce, only the infrastructure remains. The most fascinating mystery surrounds the ancient transport road itself. Archaeologists discovered a carefully engineered route connecting the quarry to the shores of the ancient Lake Moeris region. The road crossed difficult desert terrain and appears specifically designed for hauling heavy stone loads. Unlike ordinary pathways created through repeated use, this route required planning before construction began. Engineers had to identify a corridor capable of supporting repeated transport of multi-ton blocks while minimizing risk and energy expenditure. This immediately raises one of the greatest unanswered questions in ancient engineering. How did Egyptian surveyors map the landscape? Modern route planners rely on topographic maps, satellite imagery, aerial photography, GPS systems, and computer modeling. Ancient Egyptians possessed none of these tools, yet the route selected at Widan el-Faras demonstrates a sophisticated understanding of terrain. Excessive gradients would have made transport impossible. Soft surfaces could trap sledges. Sharp changes in elevation would dramatically increase labour requirements. Somehow, ancient surveyors identified a viable route across kilometres of desert while optimising for efficiency. The methods used remain poorly understood. Some researchers proposed that teams conducted systematic ground surveys using simple sighting instruments, measuring ropes, and observation points. Others suggest generations of accumulated practical knowledge allowed ancient planners to recognize optimal terrain intuitively. Yet even these explanations leave questions unanswered. Modern engineering studies show that hauling heavy loads often requires careful calculations involving friction, slope, load distribution and traction. The transport route at Widan el-Faras appears too effective to be the product of random trial and error alone. The challenge becomes even more impressive when the properties of basalt are considered. A block measuring only 1 cubic metre could weigh nearly 3 metric tons. Larger architectural blocks would weigh considerably more. Experiments involving ancient-style sledges indicate that moving such loads requires substantial manpower. Research conducted on ancient Egyptian transport methods suggests that reducing friction through water lubrication can significantly decrease pulling forces. Famous tomb paintings show workers pouring water ahead of sledges carrying colossal statues. Whether similar techniques were employed at Widan el-Faras remains uncertain, but the scale of the operation strongly suggests advanced knowledge of mechanical principles. Another puzzle emerges from the unfinished blocks still scattered across the quarry. These abandoned stones provide rare snapshots of the production process. Tool marks reveal stages of extraction. Partially detached blocks show how quarry workers separated stone from bedrock. Yet, some unfinished pieces appear so large that their intended transport remains difficult to explain. Their existence raises the possibility that engineers occasionally push technological limits beyond what available infrastructure could reliably handle. In some cases, abandoned blocks may represent failures. In others, they may reflect changing construction priorities or political disruptions. The archaeological evidence does not provide definitive answers. The transportation chain extended far beyond the desert road. Once blocks reached the lakeshore region, they likely entered a river-based distribution network connected to the Nile. From there, stone could be shipped to royal building projects throughout Egypt. This process required coordination between quarry workers, transport crews, boat operators, administrators, and construction teams. The logistical complexity rivals systems associated with much later civilizations. Comparisons can be drawn with Roman imperial supply networks or the movement of granite from Aswan. Yet Widan el-Faras predates many of these examples by more than a millennium. The road itself also challenges traditional assumptions about the history of infrastructure. Historians often associate engineered roads with civilizations such as Rome, whose vast network eventually stretched over 400,000 kilometers. Widan el-Faras demonstrates that specialized transport roads existed far earlier. While much smaller in scale, the road's purpose was highly sophisticated. It was not built primarily for communication or military movement. It appears to have functioned as dedicated industrial infrastructure. In that sense, it resembles a prehistoric freight corridor designed exclusively for moving raw materials. Madauros was discovered by modern archaeologists in the highlands of northeastern Algeria near the modern town of Madauros, roughly 100 kilometers south of the Mediterranean coast. Scattered Roman ruins had long been known to local inhabitants. But systematic investigations during the 19th and 20th centuries revealed something far more remarkable: the remains of a sophisticated city that flourished on the edge of the Roman Empire. Archaeologists uncovered a theatre, baths, temples, paved streets, reservoirs, and extensive residential districts. The structures themselves were impressive, but the deeper mystery emerged when researchers began asking a simple question: how did a large urban centre sustain itself in a region with limited water resources, variable rainfall, and no major river nearby? More than 1,700 years after its peak, Madauros continues to challenge historians because many of the engineering systems that supported urban life remain only partially understood. Madauros occupied an important position within Roman North Africa, a region that became one of the empire's most productive agricultural zones. During the first centuries CE, North Africa supplied enormous quantities of grain and olive oil to the city of Rome. Some estimates suggest that provinces across the region contributed millions of tons of agricultural products over several centuries. Yet, successful agriculture required stable infrastructure, reliable water management, and careful environmental adaptation. Madauros existed within this network, but unlike cities situated along major waterways, it depended on technological solutions that are still difficult to reconstruct in detail. The most significant mystery concerns water. Modern satellite imagery, excavation reports, and topographic surveys indicate that the city possessed large public baths, fountains, reservoirs, and drainage systems. Roman baths were extraordinarily water-intensive. Even a medium-sized bath complex could consume hundreds of thousands of litres of water per day. Cities such as Rome, Carthage, and Caesarea relied on massive aqueduct systems stretching tens or even hundreds of kilometres. Madauros appears to have achieved similar urban functions without access to such obvious natural advantages. Archaeologists have identified cisterns and evidence of water collection infrastructure, but the full hydraulic network remains unknown. Some researchers suspect that substantial portions of the system remain buried beneath later deposits or were dismantled during centuries of reuse. The surviving evidence demonstrates that the water arrived. What remains unclear is exactly how engineers guaranteed sufficient supply during prolonged dry seasons. This challenge becomes even more intriguing when compared with other ancient settlements. Petra in modern Jordan developed sophisticated runoff collection systems capable of capturing seasonal floods. The Nabateans transformed an arid landscape into a thriving urban centre through channels, reservoirs, and dams. Similarly, the inhabitants of Madauros appear to have mastered local hydrology, yet the precise methods used to balance seasonal variability remain uncertain. Unlike Petra, where many hydraulic structures remain visible, much of Madauros' infrastructure has disappeared, leaving only fragments from which researchers must reconstruct the larger system. Another unresolved question involves surveying technology. The city exhibits the characteristic planning principles found throughout the Roman world. Streets align with remarkable consistency. Public buildings occupy strategically organized locations. Drainage channels follow carefully calculated gradients. Today, engineers accomplish such tasks with GPS receivers, laser levels, and digital mapping systems. Roman surveyors relied on instruments such as the chroma and chorobots. These tools were ingenious but mechanically simple. Nevertheless, Roman cities across thousands of kilometers frequently achieved levels of geometric precision that continue to impress modern researchers. At Madauros, the layout suggests advanced understanding of slopes, water flow, and spatial organization. The mystery is not whether Roman surveyors were skilled. The mystery is how such accuracy was consistently achieved across generations with limited technology and without the mathematical frameworks used by modern engineering. The city's construction materials introduce another layer of uncertainty. Many surviving walls remain standing despite nearly 2 millennia of weathering. North Africa experiences significant temperature fluctuations, seasonal rainfall, erosion, and occasional seismic activity. Yet portions of Madauros continue to endure. This durability echoes one of the most famous technological puzzles of the ancient world: Roman concrete. Scientific studies published during the 21st century revealed that certain Roman concretes contained self-healing properties generated through chemical interactions involving lime clasts and mineral-rich aggregates. Researchers examining harbour structures in Italy have identified mineral formations that strengthened concrete over time rather than weakening it. While Madauros was not a coastal harbour, its surviving masonry raises similar questions. Did local builders adapt construction formulas to regional materials? How much practical knowledge was transmitted through apprenticeship systems that vanished centuries ago? Archaeologists can analyze the stones and mortar chemically, but chemical composition alone cannot fully explain the craftsmanship behind structures that survived far longer than many modern buildings. The theatre of Madauros presents a different kind of engineering mystery. Roman theatres were designed not only as entertainment venues, but also as acoustic machines. Many could project unamplified speech to audiences numbering in the thousands. Modern acoustic modelling has demonstrated that curved seating arrangements, stone surfaces, and architectural geometry can significantly enhance sound transmission. Yet no detailed engineering manuals survive explaining how local builders optimised these effects in every location. The theatre at Madauros follows principles seen throughout the Roman world, but each site required adaptation to specific terrain, materials, and environmental conditions. Whether builders relied on formal calculations, empirical experimentation, or generations of accumulated knowledge remains uncertain. Beneath the visible city lies another largely invisible system: drainage. Urban success depended not only on delivering water, but also on removing it. Excess rainfall, wastewater, and runoff had to be managed continuously. Archaeological evidence indicates the presence of underground drainage infrastructure integrated into the city's layout. Such systems required precise gradient control. Too steep and channels would erode. Too shallow and sediment would accumulate. Modern civil engineers solve these problems through mathematical modelling and fluid dynamics. Ancient engineers achieved comparable, practical results through methods that remain imperfectly understood. The physical channels survive. The knowledge used to design them largely does not. Madauros also raises broader questions about environmental adaptation. North Africa today is often associated with arid landscapes, yet environmental evidence indicates that regional conditions fluctuated significantly over time. Ancient communities needed strategies for drought resilience, agricultural productivity, and resource management. The city's long occupation suggests successful adaptation across multiple generations. Similar challenges confronted settlements from the Levant to the Iberian Peninsula. Some failed, Madauros endured. Archaeologists can identify the outcome but still struggle to reconstruct the complete decision-making processes that enabled such resilience. Mons Claudianus lies deep within Egypt's eastern desert, approximately 120 kilometers from the Red Sea and more than 500 kilometers south of modern Cairo. Today, it is recognized as one of the most remarkable archaeological sites connected to Roman engineering. Modern archaeologists identified the site through the remains of a vast Roman quarrying complex, abandoned settlements, military installations, roads, inscriptions, and thousands of written records preserved by the arid desert climate. At first glance, it appears to be little more than a remote quarry. Yet, hidden among the granite mountains is evidence of one of the largest industrial operations of the ancient world. Nearly 2,000 years ago, Roman engineers extracted enormous blocks of granodiorite from this harsh landscape and transported them across hundreds of kilometers to construct some of the empire's most prestigious monuments. Archaeologists can map the roads, measure unfinished columns, analyze tools, and reconstruct logistical systems. What remains difficult to explain is how Roman engineers achieved such extraordinary levels of efficiency, precision, and organization in an environment that should have made large-scale industry almost impossible. The stone itself presents the first mystery. Mons Claudianus was famous for producing granodiorite, an exceptionally hard igneous rock closely related to granite. Modern geological measurements place its hardness around 6 to 7 on the Mohs scale. Even with modern cutting equipment, extracting enormous monolithic blocks from such rock is a demanding task. Yet Roman quarry workers routinely detach blocks weighing more than 100 tons, and occasionally approaching or exceeding 200 tons. Archaeologists have identified extraction trenches, wedge holes, and partially completed blocks abandoned in the quarry. These remains reveal part of the process, but not the full technical knowledge behind it. Engineers today understand the basic principle of splitting stone using wedges, but the remarkable success rate achieved at Mons Claudianus remains difficult to explain. A single hidden fracture could destroy months of labour. Somehow, Roman quarry masters consistently identified suitable stone masses and minimised catastrophic breakage, despite having no modern geological instruments. Their understanding of rock behaviour appears to have been based entirely on practical experience, yet the sophistication of the results suggests knowledge accumulated over generations. Scattered throughout the quarry are unfinished columns that provide a glimpse into another technological puzzle. Some were intended to become enormous monolithic columns for imperial construction projects. Several examples exceed 15 meters in length. A finished column of this size could weigh well over 200 tons. What makes these objects remarkable is not simply their scale, but their precision. Roman architects demanded highly regular cylindrical shapes, because even minor imperfections became visible when columns were erected in temples, basilicas, or public buildings. Modern engineers would typically rely on advanced measurement tools to maintain consistent geometry across such distances. The Romans possessed no lasers, digital levels, or computerized surveying equipment. Yet, surviving columns made from Mons Claudianus stone display remarkable uniformity. Researchers continue debating how quarry workers maintained dimensional accuracy while shaping massive stone objects in the middle of the desert. No surviving technical manual fully explains the methods involved. The greatest mystery may be transportation. Extracting a 200-ton column is impressive. Moving it may be even more extraordinary. The quarry stood far from the Nile, the transportation artery of Roman Egypt. Massive stone blocks first had to travel across approximately 120 kilometers of desert before reaching river transport networks. Modern experiments involving ancient-style sledges suggest that moving such weights required immense force even under ideal conditions. Comparisons with the transportation of obelisks in ancient Egypt reveal similar challenges, yet Mons Claudianus operated continuously for centuries rather than as a single monumental project. Archaeological surveys have identified roads, way stations, and military outposts connecting the quarry to the Nile corridor. The existence of the infrastructure is clear. What remains uncertain is the exact engineering behind daily transport operations. How many workers were required? How were slopes managed? How were sledges prevented from failing under extreme loads? How were routes maintained despite seasonal erosion and desert conditions? Ancient records provide fragments of information, but not enough to fully reconstruct the system. Equally puzzling is the water problem. Modern visitors quickly recognize that Mons Claudianus lies within one of the harshest environments in Egypt. Summer temperatures frequently exceed 40 degrees Celsius. Rainfall is extremely limited, yet archaeological evidence indicates that hundreds and sometimes thousands of people occupied the settlement. Workers, soldiers, administrators, craftsmen, and animals all required reliable water supplies. Excavations have uncovered wells, reservoirs, storage systems, and evidence of carefully managed distribution networks. Roman engineers clearly solved the problem. The mystery lies in how effectively they did so. Maintaining an industrial workforce in such an environment required not only water acquisition but also storage, rationing, transportation, and long-term planning. Some researchers compare the logistical challenge to supplying isolated military bases in modern deserts. Unlike modern operations, however, the Romans had no pumps, trucks, or mechanized distribution systems. The settlement itself reveals another layer of technological sophistication. Mons Claudianus was not merely a quarry, it functioned as a highly organized industrial community. Excavations have uncovered workshops, administrative offices, warehouses, barracks, animal facilities, and residential quarters. Thousands of ostraka, inscribed pottery fragments used as documents, provide insight into daily operations. These records mention workers, supply deliveries, equipment requests, transportation schedules, and administrative decisions. The remarkable aspect is the scale of coordination. Every stone block represented the culmination of quarrying, shaping, transport, maintenance, food supply, water management, security, and communication. Modern industrial projects rely on telecommunications, computers, and real-time monitoring. Roman administrators relied entirely on written records, messengers, and human organization. Yet the quarry operated successfully across generations. The mechanisms that allowed such sustained efficiency remain only partially understood. Tool technology raises further questions. Granodiorite is notorious for damaging cutting edges. Continuous quarrying should have produced enormous wear on iron tools. Archaeologists have recovered evidence of picks, chisels, wedges, and blacksmithing activities, but the full metallurgy behind these tools remains debated. Roman iron production was highly advanced for its time, yet Mons Claudianus suggests levels of durability that surprise many researchers. Either tool replacement occurred on a massive scale, or Roman craftsmen possessed exceptionally effective methods of forging, hardening, and maintaining equipment. Similar debates occur when examining Roman mining operations in Spain or large-scale stone extraction in ancient quarries throughout the Mediterranean. The physical evidence proves the work was accomplished. The exact technical details remain elusive. The road system connecting Mons Claudianus to the outside world presents another unresolved puzzle. Archaeological mapping has revealed a network of fortified stations, positioned at intervals along desert routes. These outposts appear to have functioned as supply hubs, communication points, and security installations. The system resembles a logistical corridor rather than a simple road. Comparisons have been made with later imperial transport networks, including sections of the Roman Cursus Publicus and even certain early modern trade routes. Yet the quarry network predates many large-scale industrial transportation systems by more than 1,000 years. Its existence demonstrates that Roman engineers understood not only construction but also supply chain management on a remarkably sophisticated level. The ancient port of Cairnpapple is located on the Saronic Gulf, about 8 kilometers east of Corinth in Greece. Today it appears as a quiet archaeological shoreline. 2,000 years ago it was one of the busiest maritime gateways of the Roman Mediterranean. Beneath the shallow waters and scattered ruins lies a technological mystery that continues to challenge archaeologists, engineers, geologists, and historians. Cairnpapple was not merely a harbour, it was an enormous logistical machine that connected the eastern Mediterranean to mainland Greece, handling cargoes from Egypt, Asia Minor, Syria, and beyond. Yet many of the engineering systems that made this possible have vanished, leaving behind questions that modern research can only partially answer. The modern rediscovery of Cairnpapple began during archaeological investigations in the 20th century, particularly through excavations conducted by the University of Chicago and later underwater surveys. What initially appeared to be ordinary harbour remains soon revealed something extraordinary. Archaeologists found submerged port structures, sophisticated waterfront architecture, warehouses, religious buildings, and one of the most astonishing collections of ancient architectural glass ever discovered. The deeper researchers investigated, the more they realized that Cairnpapple represented a level of technological organization far beyond what many had expected from a provincial Roman harbour. One of the first mysteries concerns the harbour itself. Ancient ports across the Mediterranean often depended on naturally protected bays. Cairnpapple, however, occupied a coastline exposed to changing winds, coastal currents, earthquakes, and long-term geological instability. The Gulf of Corinth region remains one of the most seismically active zones in Europe today. Modern geodetic measurements show that parts of the region continue to experience tectonic movement measured in millimeters per year. Over centuries, such movement accumulates into dramatic landscape changes. Yet Roman engineers managed to create harbour facilities that operated successfully for generations despite these conditions. The submerged remains visible today suggest that portions of the ancient waterfront have sunk beneath sea level. Researchers continue debating exactly how this happened. Some geological models point toward gradual subsidence. Others suggest sudden displacement caused by major earthquakes. Historical records describe destructive seismic events affecting Corinth repeatedly throughout antiquity. The challenge is determining whether the harbour's current underwater position resulted from a single catastrophic event or centuries of cumulative geological change. In either case, the engineering achievement remains remarkable. Builders somehow identified locations capable of supporting massive harbour infrastructure in one of the most unstable geological environments of the Mediterranean. The harbour's breakwaters present another puzzle. Ancient engineers had to control wave energy while maintaining navigable access for ships. Modern coastal engineering relies heavily on mathematical modelling, satellite observations, and computer simulations. Roman engineers possessed none of these tools, yet archaeological evidence indicates that harbour structures at Cairnpapple were positioned with impressive effectiveness. Similar challenges can be seen at famous Roman ports such as Portus near Rome and Caesarea Maritima in present-day Israel. However, each harbour faced unique local conditions. The fact that Cairnpapple functioned successfully suggests a sophisticated, practical understanding of coastal dynamics that was never formally documented. The mystery becomes even deeper when examining the economic scale of the port. Corinth occupied a strategic position near the Isthmus of Corinth, the narrow land bridge connecting mainland Greece to the Peloponnese. Ancient sources describe the transport of ships and cargo across this isthmus through the Diolkos, a paved route that allowed vessels to avoid the dangerous circumnavigation of southern Greece. Cairnpapple served as the eastern maritime terminal of the system. The logistical complexity required to coordinate incoming ships, cargo storage, customs operations, labour forces, and overland transport would have been immense. Modern ports depend on digital scheduling systems, communications networks, and advanced management software. The administrative technologies that enabled Cairnpapple to operate efficiently remain largely invisible in the archaeological record. Perhaps the most extraordinary mystery emerged during excavations of a structure destroyed by fire sometime in the late Roman period. Archaeologists uncovered hundreds of fragments and panels of decorative glass stored within wooden containers. This discovery transformed understanding of ancient glass technology. The collection represented the largest known assemblage of architectural opus sectile glass ever found in the Roman world. The significance of this discovery cannot be overstated. Opus sectile refers to decorative compositions created by cutting and fitting precisely shaped pieces of material into elaborate patterns. Most surviving examples use marble, stone, or other durable materials. At Cairnpapple, however, the artisans worked with glass on a scale rarely seen anywhere in antiquity. Some panels measured dozens of centimetres across and displayed remarkable consistency in colour, transparency, and thickness. Producing such glass would have required extraordinary technical control. Modern industrial glass manufacturing depends upon carefully regulated temperatures, controlled cooling environments, and precise material compositions. Ancient glassmakers lacked electronic sensors, automated furnaces, and scientific instrumentation. Yet laboratory analyses indicate that Roman craftsmen could achieve surprisingly consistent results. Temperatures within ancient furnaces likely exceeded 1,000 degrees Celsius. Maintaining stability across large production batches without modern monitoring equipment remains one of the most impressive achievements of ancient materials science. The Cairnpapple glass raises several unanswered questions. Where exactly was it manufactured? Was it produced locally or imported from major production centres in Egypt or the Levant? How were such fragile materials transported across hundreds or even thousands of kilometres without extensive breakage? The Roman Empire possessed impressive trade networks, but moving large decorative glass panels represented a logistical challenge, unlike transporting amphorae or stone blocks. Even today, shipping large architectural glass requires specialised packaging and handling systems. Chemical studies suggest connections between some Roman glass and raw materials originating in Egyptian and Levantine coastal sands. Yet tracing individual pieces to specific workshops remains difficult. The possibility that artisans distributed semi-finished glass across vast distances before final shaping and installation adds another layer of complexity. Cairnpapple may preserve evidence of a manufacturing and distribution network whose full structure remains unknown. Another mystery involves preservation itself. Glass is often considered fragile, yet portions of the Cairnpapple assemblage survived nearly 2 millennia. Researchers continue studying how burial conditions, fire damage, mineral deposits, and local environmental factors contributed to preservation. Some fragments retain vivid colours and remarkable clarity despite centuries underground. Understanding these preservation mechanisms may even provide insights useful for modern conservation science. The warehouses surrounding the harbour present additional engineering questions. Archaeological remains suggest large-scale storage operations capable of handling substantial volumes of imported goods. Effective storage near a marine environment requires control of moisture, drainage, ventilation, and structural stability. Ancient builders appear to have incorporated practical solutions into their designs. but many details have disappeared. We see foundations, walls, and fragments of infrastructure. We rarely see the complete environmental management systems that once protected valuable cargoes. Water management at Cairnpapple remains partly unexplained. The port needed reliable fresh water for sailors, merchants, residents, and maintenance. Evidence of cisterns and hydraulic systems shows careful planning, but the full network is still unknown. Like other Roman engineering works, the surviving structures reveal impressive skill while hiding many operational details. Located on the northern edge of the Orv Mountains, roughly 35 kilometers east of modern Batna in northeastern Algeria, the ancient Roman city of Thamugadi lay buried beneath sand and debris for centuries before excavations gradually revealed one of the best preserved urban landscapes of the Roman Empire. Archaeologists initially expected to uncover a typical provincial settlement. Instead, they exposed a city distinguished by its remarkable precision, advanced engineering, and sophisticated infrastructure, features that continue to raise questions about technological capabilities that remain only partially understood nearly 2,000 years after its construction. Founded around 100 CE by Emperor Trajan, Thamugadi was originally designed as a colony for Roman military veterans. What makes the site remarkable is not merely its survival, but the almost mathematical perfection of its urban plan. From above, the city resembles a giant geometric diagram carved into the landscape. Straight streets intersect at nearly perfect right angles, forming a grid whose accuracy rivals the planning seen in many modern cities. The central district measures approximately 355 meters on each side, creating a remarkably regular square layout. Today, archaeologists can map every street using satellite imagery and laser surveys. Yet, an important mystery remains. How did Roman surveyors achieve such precision without modern instruments? Ancient sources describe a device called the groma, a surveying instrument used to establish straight lines and right angles. However, experimental archaeologists have demonstrated that maintaining alignment across hundreds of meters of uneven terrain is considerably more difficult than simple descriptions suggest. Even minor errors accumulate rapidly. Yet many of Thamugadi's streets remain aligned with astonishing consistency. Comparisons with medieval European towns reveal a dramatic difference. Most medieval settlements evolved organically, producing winding streets and irregular blocks. Thamugadi instead appears to have been planned according to a highly disciplined geometric framework from the very beginning. The city raises the possibility that Roman surveyors possessed practical field techniques far more sophisticated than surviving texts indicate. The mystery deepens when examining the city's expansion. The original colony was designed for perhaps a few thousand inhabitants. Over time, the population grew far beyond the limits of the initial enclosure. New districts spread outward, temples appeared, markets expanded, and public buildings multiplied. Yet many later developments maintained a surprising degree of organizational coherence. Urban growth in most ancient cities eventually produced chaotic street networks. At Thamugadi, planners somehow managed to preserve order across generations. The administrative knowledge required to coordinate such expansion has largely vanished. Archaeologists can reconstruct buildings, but they cannot reconstruct the manuals, calculations, or planning procedures used by the officials who organized the city. Water management presents another technological puzzle. Thamugadi existed in a semi-arid environment where reliable access to water determined whether urban life could flourish or fail. The city contained baths, fountains, drainage systems, and distribution networks requiring continuous water supply. Roman engineers are famous for aqueducts such as those feeding Rome, where some channels maintained gradients as low as a few centimeters per kilometer. Similar principles appear at Thamugadi. Streets and drains were carefully graded to move water efficiently while minimizing erosion. Modern engineers understand the mathematics involved, but the challenge lies in explaining how ancient builders repeatedly achieved such precision without laser leveling equipment or modern surveying tools. Beneath the streets lies an equally impressive drainage network. Excavations have revealed underground channels capable of carrying wastewater away from residential and public areas. These systems required careful calculations of slope and capacity. Too steep and water would damage the infrastructure. Too shallow and blockages would occur. Some sections continued functioning for centuries despite fluctuating populations and environmental changes. Researchers can measure the surviving structures, but the practical methods used to design them remain poorly documented. Like many Roman technologies, the physical evidence survives while the operational knowledge has disappeared. The durability of Thamugadi's construction materials introduces another unresolved question. The city endured nearly 2 millennia of environmental stress, including temperature fluctuations, seasonal rainfall, earthquakes, and human activity. Many walls, arches, and foundations remain standing despite centuries of neglect. Studies of Roman construction elsewhere have revealed sophisticated use of lime-based mortars capable of developing exceptional long-term strength. At sites such as the Pantheon in Rome, researchers have discovered self-healing properties within certain Roman concretes. Although Thamugadi relied heavily on local stone rather than monumental concrete vaults, the longevity of its masonry suggests builders possessed a detailed understanding of materials science based on generations of empirical experimentation. One of the most intriguing examples is the city's famous Arch of Trajan. Rising approximately 12 meters high, the structure has survived remarkably well despite its age. Engineers studying Roman arches recognize that their strength depends on precise geometry and careful distribution of compressive forces. Small deviations can compromise stability, yet Roman builders repeatedly created arches that endured for centuries. Modern structural analysis explains why these monuments stand today, but it does not fully explain how ancient craftsmen consistently achieved the necessary precision in an era without advanced measurement technologies. The city's public architecture also reveals evidence of complex logistical capabilities. Thamugadi eventually contained theatres, baths, temples, markets, libraries, workshops, and administrative buildings. Constructing and maintaining such infrastructure required coordinated labour, material transport, financial administration, and technical expertise. Historians often focus on monuments because they survive physically. The greater mystery may be the invisible organizational systems behind them. Every building required supply chains, training programs, skilled specialists, and administrative oversight. Comparable logistical complexity would later characterize major medieval and early modern cities, yet Thamugadi achieved it during the height of the Roman Empire nearly 2,000 years earlier. Archaeologists have also become interested in the city's relationship with its surrounding landscape. Satellite imagery reveals traces of roads connecting Thamugadi to regional trade networks. These routes link the colony to agricultural production zones, military installations, and commercial centres throughout Roman North Africa. Similar transportation systems supported major cities such as Carthage and Leptis Magna. The challenge lies in understanding how administrators coordinated the movement of food, stone, timber, metals, and manufactured goods across vast distances. Ancient records mention taxation, trade, and transportation, but they rarely provide the technical details necessary to reconstruct the full logistical system. Another puzzle concerns urban resilience. Many ancient cities declined rapidly when political or economic conditions changed. Thamugadi remained occupied and functional for centuries. This longevity suggests that its infrastructure possessed a degree of flexibility and adaptability. Water systems could be maintained, buildings could be repurposed, streets continued serving changing populations. Modern urban planners recognize resilience as a key indicator of successful design. The fact that Roman engineers achieved it so consistently remains a subject of ongoing study.